Final comments, and I wanna just wrap up by saying flat earthers only constructive comments, information. Anyone that attacks Sandy, I'm going to ban you, and you're never going to be able to comment on my channel again. All right. Hello, everybody. This is going to be a fun, interesting podcast. Today we have with me my co-host, Angels of Light from TikTok, and we're going to be talking to Sandy, who's from the Republic. Give me the full name of your site, the Republic of America?
Republic for the United States of America.
Republic for the United States of America, a true patriot. Sandy was in the military. She can tell us a little bit about that. And we're going to start off today on this show talking about our views on the Earth, the shape of the Earth. Sandy thinks that she has proof that the Earth is a globe, like we all did, and we're going to go from there. Sandy, I just want to bring up one thing. Have you ever been wrong in your life? Of course, we have, and the answer is sure. And so we're going to present stuff today that I really want your opinion on. I want you to, maybe we're both going to learn something new, but we're going to see where it goes from there. So you good with that?
We'll give it a try.
Okay.
I did watch the video you recommended.
Oh, so that was Flatten the Curve by Vic Adrazi about the military people. What did you think of it?
I had a migraine by the time I got halfway through because of all the mistruths that they were speaking.
Oh, okay.
That was pretty much in summary.
All right.
I was going to share that with you off screen, but
no, that's okay. We're honest here. We're all friends, and at the end of the show, if we don't agree, we're still friends. We're still on the same team, and we all have our ideas what this place is. I think that this topic is the most important topic because if you're not grounded, if you don't know that we're at the center of creation, I think it weakens your ability to live to your full potential. That's my belief. Let's see if we get there. Angel, you want to say anything before we start?
Not really. We can just get right into it, I think. Yeah, we're good to go.
All right. So Sandy, why don't we start with what would you believe we live on a spinning globe? What would your number one reason for that being? Is that a good question?
That's a good question. There's so many to pick from. Probably what causes things to stay on the Earth is probably the biggest difference between globe Earth theory and flat Earth theory.
Okay.
Right? Because, someone did the math and said that it's, flying through space at this speed and it's spinning at this speed and there's no way things could stick to it. And I'm like, yeah, there is.
Well, how do things stick to the Earth?
Well, gravity is a construct. It's a theory also.
Okay.
Everything in science is a theory. There's no absolutes. And so I'm a pure scientist. So
okay.
Flat Earth theory has a possibility of being true. I cannot say it's zero.
That's nice.
I can never say that about any theory.
Okay.
And I also can't say that globe theory is 100% truth. I can't say that either. So I've always had an open mind about all, especially things that go against the common grain. It's like I've always been one of those underdog kind of, not following the rules kind of guy.
Let me ask you a question. So is a helium balloon an anti-gravity device, or is it just less dense than air?
Pretty much just less dense than air.
Right, and a rock is more dense than air, so it seeks equilibrium the other way. Right, so we've got an electrostatic gradient in the atmosphere constantly discharging to the Earth, creating its small downward bias.
Mm-hmm.
And then the force of buoyancy supersedes that to determine directionality. It's called Archimedes' principle.
Okay.
So on the flat Earth, we have this crazy notion that angels in Australia, over there somewhere, that down is down for all of us.
Mm-hmm.
Right. On the globe Earth, people think that down is towards the center of the Earth. So people are standing antipodal to each other while spinning, while orbiting, while doing all the other motions, versus a flat stationary Earth where down is down for everybody. The question is, if I drop this, it's because it's more dense in the air, it falls down. But if I snap my fingers and the entire Earth disappeared and I let it go, which way is it going to go? Right? Which way is down? There is no down. Well, the Earth is, everything is electrostatically charged. Everything. You agree with that? Air, food, people, rocks, everything has an electrostatic charge to it.
It would be really hard to declare something at neutral zero charge.
Okay.
One electron off.
Yeah. So the ground has a testable, measurable, neutral or negative, depending on how you look at it, charge, and anything above the ground is surrounded by the positive charge of the sky. So if the ground's not moving, the electrostatic flow is downwards, and it's a weak force, right? It's weak. But you know what they say? Gravity's weak too. But the same people that say that the electrostatic force is 10 to the 36 power stronger than gravity. Mm-hmm. So we can manipulate the electrostatic force scientifically, right? And I'll just show you real quick. We were talking the other day. I think I might have showed you this, but let me show it real quick. So we got these helium balloons. This button is neutrally buoyant off the floor. The wire goes to a Van der Graaf generator. We're going to introduce a higher positive charge to this. It has its natural positive charge. We're adding a little positive charge. And when we do, we just manipulated our independent variable and it goes down. And then when we discharge it, it goes back up. And so what's the opposite of that? The opposite of that is if we took something, we put a negative charge into it, it goes up. We turn the negative charge off, it goes back down. You turn it back on, keep it on, it goes up. So we are playing and proving that electrostatics is real. Can you name a test that has proved gravity, that has isolated the electrostatic field from the cause?
I think it's Cavendish experiment.
But he didn't eliminate the electrostatic field. It went over a course of days. The sun and the moon were traveling through the sky, leaving it completely open to all sorts of electrostatic forces, right? The sun and the moon are the anode and cathode of our battery system. The salt water carries the current. The land is a salt bridge. Go ahead, Angels.
Yeah, Cavendish didn't even isolate gravity. He didn't manipulate gravity at all. It just assumed gravity's real with two balls and they attracted, right? But it's funny because we're not even talking about your current paradigm's belief in gravity right now. It's the bending and warping of space-time. It's not Cavendish isn't proving the bending and warping of space-time anyway. And the only other thing you have is LIGO, where they got a thousandth of a proton shift. When they just said, "Oh, it's a gravity wave." Like like I can clap my hands and make my wall vibrate more than that, right? So yeah, it's a complete joke. Yeah.
This is at MIT. This is an electrostatic drone. It has no moving parts. It's called the silent drone, and they can maneuver it up, down, left, right. They can make it fly using electrostatics. So are they defying gravity? Or are they just defying the testable, repeatable, scientifically provable electrostatic force versus defying the theory of gravity, which has been disproven 96%, which is why they came up with dark matter and dark energy?
Oh, but now you're mixing metaphors on that one, because I don't believe in dark force or dark energy and dark matter either. Well, maybe dark matter to explain some things, but dark energy, I mean, all that stuff about trying to prove the Big Bang, that's like, patting your head and rubbing your tummy at the same time to get it to work. I've never had much faith in that particular theory.
Yeah. Well, that's the current God paradigm.
That also goes back to there's a decision where you have to pick one of the roads in the fork, and it's how do you explain redshift, which is why do we see stars with particularly higher redshifts than, and it seems to be with distance, if it's farther away, it seems to be having more redshift. Of course, that doesn't work with stars stuck to a dome, but we can actually see that, in a telescope. So the theory being that, oh, they must be moving away from us, kind of like a train that goes, right? And you hear this change in frequency, and that's the same thing with light. That's the first fork. But what if you take the second fork and there's something else causing this shift in the light and it has nothing to do with motion? So, you're talking to someone here who's probably in the 5% of physicists who don't actually believe that the Big Bang Theory is correct the way it's written. Especially now when they're doing the patting the head and, rubbing the tummy at the same time with the dark energy thing. So
you want to address that?
Yeah, I mean, the stars physically get further away from us when they set because they move away, just like the sun. So,
mhm. Right, but we can see the redshift anywhere we look in the sky. We can look straight up and see the stars far away that have a bigger redshift. We could look out to the side and we could see stars farther away that have a redshift. And then the ones that are closer, it's all over. So it's not like it's only when we look at the stars at the horizon have a bigger redshift than the ones that we look up straight ahead. There's no correlation to that. It's purely by.
well, I don't know. I don't know how that proves a globe really anyway.
No, it
I
doesn't.
mean, it's not
We're
even,
just talking about bits and pieces
Yeah.
of all the different theories here.
Right. So this
But
star is 211 trillion miles away, but I'm
mhm,
able to zoom it in and make it fill up my camera. So let's just take a look, because you have to assume that stars are the distances that they tell us. So if we
mhm,
take a look at this, when you look up at the star Sirius, it's like this size compared to the star Orion, which is smaller, right?
mhm,
And so I can zoom in and make it this big on my P1000 zoom, right? It's 8.6 light years away, which is 50 trillion miles. So if something's 50 trillion miles away, how does my 125 zoom make it this big? Now, hold on to that. Let's just assume that it can. So now I want to look at Orion, and I can make it almost the same size. But Orion is 52 million times farther.
mhm.
So it would have to be 52 million times bigger. And it's not. So these
Area
are
square
just
law,
things
that's not gonna work,
that
but
are
keep
the
going.
fact that I can zoom in on something
Mhm,
and make it big shows that it's not the distances they're telling us. And then
well,
I
also,
go ahead.
with the sun and moon, like, you can zoom in on the sun,
mhm,
and have a manual focus. And then you can use that same focal length, look at the moon, and
mhm,
they're still in focus. But one's supposed to be 400 times further away.
mhm,
Even during a lunar eclipse, or sorry, a solar eclipse,
mhm.
you see the moon going over the sun.
Right.
They're both in focus with the same focal length. So
Mhm.
yeah,
Well,
and even
it's
when
almost indetectable because when you're looking at the camera and you see what the little numbers are that are on your focal length, I'm a photographer too. It's infinity, which is when you get past a certain distance,
Right.
the distances between really far things is like really tiny amounts in that, focal distance of that infinity range of the camera. So I've seen that myself. I've done the same
So
thing.
So,
Just
Sandy, you're saying redshifts makes you believe that these stars are going farther away, but you agree that there could be a different explanation why we see redshift, right?
Oh, I'm pretty sure because I
Okay,
don't think the Big
so
Bang Theory really
my
makes
my point is, what are stars made from?
according to the theory, basically hydrogen.
Hydrogen and helium, and basically
Well,
which defy
yeah.
gravity here on Earth, and gas
What
laws. What's that? Sorry.
would you say at the end?
I said helium and hydrogen. It's like they tell us our sun is made up of 98% helium and hydrogen, or 99%.
Something like that.
Yeah. So helium and hydrogen are gases. And we know that if we had a box of gas, any gas, air, gas, whatever,
Mhm.
and we put it into a room with lower pressure or no pressure, it's going to violently expand as soon as we give it the ability. It's going to violently fill and equalize, correct?
To a point, because gravity is also taking effect, its mass. And
So,
we're actually talking about a plasma sun because it's so hot. We've just got hydrogen atoms and helium atoms,
yeah.
and the electrons are in a plasma soup, for more of lack of a better word.
So how do stars form?
Well, that theory goes that it's a gas cloud, yeah, your Orion Nebula kind of thing.
Hmm?
And there's always stuff moving.
So
So,
let's talk about this. So a
uh,
nebula is gas and dust in a space vacuum.
mhm.
That's a problem. And then some of the gas and dust, enough of it gets together where it attracts more, where it attracts more, it attracts more, and it starts collapsing onto itself.
Mhm.
And that's how it forms a star the size of our sun, which is tiny compared to like Betelgeuse, which is thousands of times bigger. And then there's other ones, crazy names. So what stops what? So let's say a star is forming in here.
Mhm.
Uh, what stops the star from forming any bigger? It says, okay, I'm at the right size. Does it pop out and then go park itself somewhere in the galaxy?
No, it starts to ignite and it goes to
It,
nuclear fusion
all right, it goes to nuclear fusion, but why doesn't all the other gas in the nebula just make one giant star?
because the fusion then creates the solar wind, which then pushes out a lot of the stuff that it would have absorbed.
So when it gets to the size of our sun, it
Mhm.
starts pushing things out and then it ejects itself and parks somewhere.
No, it stays right where it was, pretty
So,
much.
so nebulas form stars that all stay within the nebula.
Well, the nebula gets blown up away eventually, and so you're just going to have the stars.
Angel.
Well, this is all like, okay, so this is all just violating all the gas laws and the second law of thermodynamics. You can't have a large amount of gas in a vacuum. And I
Sure.
could show you a little presentation now demonstrating this.
Hmm.
Gases move randomly in all directions. They don't have a bias for down. Right. If I could just share my screen real
Good,
quick.
good, you're good.
Well, that is violated by the observations of our atmosphere. Our
Yeah,
atmosphere is
well,
denser at the surface than it is at the mountains, which it is at the 40,000 feet or 100,000 feet. So it is pulled
it,
in.
it no, it's just the only way to have a gas pressure gradient, which is what you're talking about,
Mhm.
is within a container, right? And the molecules throughout the whole atmos are all moving in randomly in all directions, right? So this is NOAA.gov. The atoms and molecules that make up various layers of the atmos are constantly moving in random directions.
Mhm.
Hang on just a sec. Kind of move this. Um, so this is a gas pressure simulator from Colorado EDU. Right,
Mhm.
they move randomly in all directions. Then we got states of matter Purdue University.
Mhm.
The gases are well separated with no regular arrangement. They
Mhm.
assume the shape and volume of their container. And then we've got the kinetic theory of gas, and they always draw a container for the gas molecules
Mhm.
because that's the only way to have gas pressure. Because it's defined as the amount of force exerted by the particles on the walls of a container, and they are in constant random motion, not in constant downward motion, right? So imagine this though. If we're inside of a car and I've sprayed these gas molecules in the car, they spread out in all directions and fill the car up. Now, if I open the sunroof, they escaped. You would agree with that?
No,
They
because
wouldn't escape.
you would suffocate if that happened.
No, we're not in
No,
space. We're not in space.
no, we're in the
We're
car, the
just in a
sunroof.
contained area. He sprayed some perfume. It smells in the car. He opens up the sunroof. They'll just mix with the atmosphere.
Yeah, over time,
Yeah.
it'll the air molecules will come into the car and the
Yep.
air molecules in, so it'll be an exchange
Right.
over time.
Let me throw this in, Angel. So let's take that car and we put it into a vacuum chamber, but we haven't evacuated any air at all, and we have everything is at room temperature. The closed car is at the same air pressure as the room that it's in,
Mhm.
and so we open up the roof, and there's nothing's moving around, so the air is kind of just it'll slowly exchange, but there's no breeze or anything, so it's not really intermixing very much. There'll be a little bit mixing, but if we started sucking the air out of to lower the pressure in the chamber by any fraction of any percent, the air in the car will start equalizing. It'll equalize equally, right? You can't. What's that?
It will try to. It will go the process. Yes.
It will equalize, and every experiment will show that. But you believe somehow we have a gradient that goes up to a vacuum of space, and it just sits there and it doesn't equalize because of gravity. But gravity, if I lower the air pressure in that room, gravity should hold the air in the car under your theory, but it doesn't. It won't. It'll equalize. Gas pressure always equalizes.
No. That's basically because the velocity of the particles is way faster. If you were to bring the car and the vacuum chamber, so the two of them, down to almost absolute zero, which would be really hard to do, but you could, okay, theoretically, right? So we go to absolute zero where how do we measure temperature? Well, it's the velocity of the particles. And so if you bring to get to a helium liquid or a hydrogen liquid, you're going to get really, really cold, okay? And so you've got this, this kind of motion in the particles, and so gravity still has a tiny effect on that, but that's like, this much.
Gravity is going to hold the liquid.
It's all moving because it's really hot compared to, where it should be. Now you start bringing the temperature down, and now the molecules are slowing down.
I agree.
And you're going to start seeing this gravitational effect because this randomness is being overcome now by the gravity. See, one of the things that Flat Earth says is, why didn't we lose our atmosphere? Because it's, not not enclosed. We are losing our atmosphere. But we're also gaining some atmosphere because we are moving through space. We get hit with stuff. We get, cosmic dust, meteors, the comets that go through. We got water molecules and everything, and they're all falling back in while we're losing the ones that are on the outer edges.
Good, Angel.
So you're regaining gases in a vacuum. Wow.
We're hitting them.
So in a vacuum.
Hold on, Sandy. You're making that claim.
No. See, you're claiming that there's nothing in space.
No, you guys claim that.
No, we don't claim that at all.
No, absolutely not true.
So is space lower pressure? Is space lower pressure than Earth, than our atmosphere?
Yeah.
How much lower?
Well, when you go to temperatures, I believe the current amount is something like 3.9 degrees Celsius, 4 degrees Celsius.
It's in space.
In space.
Let's say in space. Could I breathe?
Nope.
Why?
Because there's not enough oxygen because it's very, very, very far apart.
Can you show me an experiment other than reifying with saying that the Earth is losing atmosphere to space? Because that's just a theory that you've been told. You've never experienced a molecule leaving Earth or entering Earth. You've just been told that. Can you show me an experiment with high pressure next to low pressure without a container? Now, we do live in a dynamic system, and it's colder on the top of Mount Everest where the pressure is lower, and it's hotter in Death Valley where it's closer to the Earth.
Well, could you recreate a gas pressure gradient in a container using gravity? Because we can recreate a gas pressure gradient in a container using temperature and introducing a dynamic system, which is what we claim. Well, that's why we have a gradient, because the Earth is a dynamic system. But you can't prove your claim, sadly, about even if we give you a container to use for the gas pressure, you can't manipulate gravity to cause those molecules to go down.
Sure.
Or
if I get it close to absolute zero, it will definitely do that on its own.
Well, yeah, but you can't manipulate it to prove it. You're saying that the only thing in reality that has a pressure gradient due to gravity is the Earth, but you can't prove it. It's words,
Well, there's a lot of things in both theories that are hard to prove or impossible to prove unless you're there.
Well, I can show you a gas pressure gradient inside of a container right now.
I have an idea of how I can disprove the electrostatic theory of gravity. The flat Earth version of gravity being the electrostatic theory. I just need to contact my local community college and get to borrow a couple of pieces of equipment and I'll video it. I don't know when I'm going to have time to do that, but I'm pretty sure I can do this.
Well, could you manipulate gravity to make objects float or fall faster to prove your claim?
Technically, by the current theory, anti-gravity is not something that we can create.
Exactly. So
That would require negative
theorized.
mass, and we don't currently know about anything with negative mass. But we also didn't know how to do a lot of things 100 years ago, and now we do. So is it possible that we just don't have that knowledge? That's kind of where I'm parked, for belief.
Yeah, okay, cool. Now, see, you were in the military. Did you ever do anything to do with aviation or anything like that?
I was a test pilot.
Okay, well, pilots and planes, they don't adjust for curvature or earth rotation ever, right?
Every time you fly.
Nope.
Yep.
How so?
Nope.
You don't perceive it. The
Well,
aircraft is designed to fly at a certain, best speed or whatever, cruising speed, however you want to look at it. And I can fix my attitude indicator to say anything I want. There's nothing that tells me that I can't, mess with it. It's stupid because it's a backup. It's, in case I can't see, I want to be able to know if I'm right side up or upside down.
Right, so let me ask you a question. The
Sure.
attitude indicator, it maintains rigidity in space, correct?
In a perfect world, yes.
Okay, great. So, and when you do actually nose down, nose up, or bank, it will show that on the attitude indicator, right?
If it's working properly, yes.
Right. So in straight and level flight, if you were to travel, say, halfway across the Earth and you landed, would the attitude indicator show that it's nose down when you land, or would it be exactly the same as it did when you took off?
It's going to follow the curvature of the Earth, and it's going to show you relative. Yeah, I've seen it. I mean, I've got 3,800 flying hours. I've been to 45 countries all around the world in just about every time zone. So,
Sandy, a minute ago you said that the attitude indicator holds rigidity in space, and then we said, all right, when you get halfway around the world, it's now vertical to the Earth, right? So we got the Earth, and we got our this. We got our gyro. It's spinning. We take off.
I followed what you were saying.
Yeah, but you're saying it follows the curve of the Earth, so now it doesn't hold rigidity in space.
Well, it depends on how you define space.
Well,
see, for me, the space is the aircraft. Well, and the aircraft is flying through a gravity field, and so it's going to follow a gravitational.
Hold on. Gyros are not affected by gravity by definition. They're not affected by gravity. If I got the gyro and the airplane turns left, right, up, down, the gyro stays rigid. The gyro stays exactly where it is, no matter how I turn.
So now you're saying that friction doesn't exist.
Oh,
that attitude indicator will shift. It will start to drift if you don't have electricity.
Okay, but
we have electricity.
Sandy, so when you're flying, how often does the pilot need to nose down to adjust for that curve?
It's always nose down.
No, it's not.
Yeah.
It's actually a 2-degree nose up. That's how they maintain lift. I can show you the pitch data.
No, I get it. I've got half of an astronautical engineering degree. So I can set that anywhere I want. So what if the aircraft is supposed to be at 3 degrees nose high?
Exactly.
And now I'm at 2 degrees nose high to stay in an arcing motion.
You're saying you're nosing up to nose around the globe.
No.
So if the nose is always up, how is it going down around a curve?
How do you land with a nose up?
That's proving my point. I'll show you.
You have to have the nose up in order to land in most aircraft.
I agree. I agree.
We agree. Hold on.
Yeah, I agree. So this basically is a flight simulator, right? And we have, hang on just a sec. Oh, did I lose it?
No, you're here. I see it.
I see it. Okay, good. So that's the attitude indicator, and we can set the reference frame to the Earth. But in reality, I've debated many pilots. They all admit they don't need to nose down ever, right?
They don't
And if
know
they,
they're nosing down. That's my point. They are doing
okay,
it every single day, and they don't know they're doing it. In fact, the
but the thing
people on
is,
the pilots on
yeah,
that video are misspeaking so many things. It was very frustrating to listen to.
but
But
the
anyways,
thing
continue
is,
with your argument, please.
yeah, the thing is that they fly with a 2 degree nose up, and they maintain that 2 degree nose up. We've got the pitch data to support it. They never
Not
nose
every
down.
aircraft, but okay, keep going.
Yeah, so to maintain lift, this is a globe Earth. This is the dimensions of the globe. And as this plane would fly over that globe, right, obviously the ground would dip down and away from the plane constantly, right? So it's going to maintain that 2 degree, okay? And now if I aligned it to gravity, because that's what you just said, right? It just aligns to gravity. But if I speed it up now and put a pressure level on, the plane, it's going to maintain the same pressure altitude, but
Right.
eventually, see how the pitch is, it keeps gaining pitch now? Because it's not actually adjusting nose down. You're saying it does, but that would show up on the pitch data. If I was to actually nose down now, that would show up on this pitch data on the bottom here. See that? How I'm nosing down? And yes, absolutely, you're right. On a globe, I'd have to nose down. But what happens in reality, now that this is a flat Earth model, right? So I'll just stay at a 2 degree nose up to maintain lift, right? And like you said, yes, we can land nose up, obviously, because the plane and the ground always remain parallel to each other. So if I want to come in and land now, all I've got to do is nose up and land, right? I don't need to do anything because the land is still parallel, the ground is still parallel to the plane. And that's when you fly, the horizon in front of you will never drop down and away from the plane constantly. It'll just stay where it is. They've admitted that to us. And I've got the pitch data. I can show you the pitch data.
No, I'm totally following you, but I can take that attitude indicator and I can jack it up to 10 degrees nose high, and it's still going to fly straight and level as long as I realize that 10 degrees nose high is straight and level.
Absolutely. But it's not going around the curve of the Earth. If it was it's going to land, it would go around, and now it's going to be just, it's not going to keep compensating for the Earth. So when you're coming into an airport, you have to calculate your rate of descent, right? Your angle of descent. So 125 miles out, you're at 30,000 feet. You have to figure out how many feet per mile to descend, right? How do you calculate that?
You figure out you're 120 miles away. You've got 30,000 feet to lose, and you do a feet per mile calculation, convert that to an angle.
Yeah. So 125 miles out, you figure out the feet per mile, and you can land on the runway, right? At what point do you calculate the extra 2 miles of Earth curve?
Because you're 120 miles out?
125 miles out is 2 miles of Earth curve.
Okay.
So
you have to do that math to confirm it.
So all right, point taken. But according to the globe Earth, with a radius of 3959, that at 125 miles, it's about 2 miles of curvature. So you just said that you did a calculation, a flat Earth calculation, but when you get there, the runway is going to be 2 miles lower than you expected.
Well, it's not like you close your eyes at the 120-mile mark.
What if it's bad weather and it's nighttime?
Get to the runway and you're like, oh, it's not where it's supposed to be.
What about
it's adjusting it the entire way down?
Nighttime, raining, and cloudy. You're calculating your descent rate on a flat Earth calculation. You're not calculating in Earth curve.
It's happening automatically.
It just happens automatically, magically. Which device does that again?
It's called your altimeter.
Your altimeter is just measuring how high you are.
Correct, but it's by pressure altitude. So
when
you've got two kinds of altimeters.
I'm flying through a dynamic system, and there's storms. Pressure's changing constantly. So is the plane going up and down to maintain the same pressure, or is it trying to come down at a rate so it finds the runway right where it's supposed to be on the flat Earth.
If you're flying through turbulence, you're going to have some pressure changes and you are going to see your altimeter jumping around a bit, but it's not going to be hundreds or thousands of feet.
What about 2 miles of feet?
You're always adjusting. And the other thing too is if I can't see the ground, then I'm following an electrical signal to that runway.
Right.
And
So
I don't even know that my nose is slightly lower than what it would have been had I not adjusted for the round Earth.
So can I ask you a question? If you were to come in to land on a north to south runway at the equator, would you be taking into account Coriolis and the Earth's going to shift underneath the plane perpendicular?
I always love when the flat Earth people bring up Coriolis because that's not what we bring up as Coriolis.
Well,
So,
that is
yeah,
Coriolis.
oh, I know it is. I know it is. But
So
by definition, Coriolis is why there's different wind speeds at different latitudes. Because
no.
the flat Earth theory does not explain why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere.
Actually,
So you're saying it does, but what are you saying that the Earth, the Coriolis effect, which is the apparent deflection of an object in a rotating system, is causing is the Earth's rotating underneath the hurricane to cause that? That's what you're claiming.
The fact that the air at the equator has to go faster in order to stay in equilibrium with the air at the lower latitudes, higher latitudes, then is going to cause the deflection because you've got a faster velocity air at the equator and a slower velocity air at the higher
so
latitudes.
But winds move in all directions, and we've got jet streams and trade winds that go opposite directions always. So
yeah.
if the Earth is only spinning one direction, you can't claim that.
And
Sure.
Sandy, that the Coriolis is, let's pretend it's a super calm day and it's a dead air. There's no air movement. Because it's all rotating perfectly with the Earth on a globe. Around the equator, so you're moving 1,034 miles per hour, but the air is moving in lockstep, so there's no breeze and it's hot because you're on the equator.
Right.
And so you fire a bullet or whatever, and you fire it north. Well, as that bullet goes, or whatever it is, whatever you're shooting, let's say it even goes farther, the Earth is going to be spinning slower, but that bullet has that tangential speed of 1,034. So that's what's going to cause the apparent deviation, correct? That's what Coriolis is. You aware of that?
If you've got a high enough velocity and a high enough angle,
Yeah.
it's the same like ICBM missiles. That's why you have to correct for ICBMs.
Sure.
They're in the air so long that there is a significant amount of shift because the Earth is
And
spinning.
you go right after.
Okay.
Good.
You just said that the missile adjusts for Coriolis, but the plane doesn't.
So a missile is not manned, and so it has to be adjusted in order to get there where you want it to go. You
Right,
essentially are giving it its initial, where are you going to aim,
So it is adjusting for Coriolis, but again, the pilot won't be.
Always. They're always adjusting for Coriolis. They just don't realize it because it's a small enough effect.
Okay, but you just said a bullet is affected by a sniper rifle, which is in the air for 2 seconds.
Right?
Is that true?
Yes, but how much is Coriolis going to affect it in 0.2 seconds?
Well, that's not my claim. I don't claim it even is affected by Coriolis. I claim that there's no Coriolis.
And the longest bullet rifle shot was over 4 miles just about 2 years ago, less than 2 years ago. And the guy that shot it said he never calculated for Coriolis. It was in the air for some 20 some odd seconds.
We would have to calculate how much Coriolis there should have been in 20 seconds. We would also have to find out which way he shot. Was he shooting east-west or north-south or something in between?
Right.
It's all going to matter.
Sure. So Sandy, you know, even like how your paradigm claims that at the equator, the Earth is spinning east 1,037 miles an hour. So if we put a plane flying at the equator east, same direction as the Earth is spinning, but the plane's only going to go 500 miles an hour, so half that speed, will it lag behind or will it keep up?
No, that's because the air is going with it, and your airspeed means it's the speed with regards to the air.
Right. So then if we turn around, is it going to have 1,000 mile an hour headwind, or is it just going to have no headwind?
So I've done both. I have gone due east, I've gone due west. Depends upon the time of day. It can really suck because you're going right into the sun. And
Right.
so what I can
Because
tell you
that's the
is,
thing. Our position is that the plane just flies and treats the Earth as stationary, which is what we observe.
Which
We
is
don't
what you
observe
do.
Coriolis at
What you
all.
do, you don't adjust for Coriolis. You say it's happening automatically. You can't tell us how. It's because it's not. The Earth is stationary. So the things that you're describing actually work perfectly on a flat Earth with no excuses. The globe has constant excuses. Let me ask you a
no,
question.
no. So how do you get someplace if you've got a direct crosswind?
You fly into the wind. You know, if you have a
Yeah,
headwind of
you
200
have
miles
to.
an
So
hour,
instead of flying straight, you have to fly slightly crooked into the wind
sure,
so
wind.
that
Absolutely,
you're actually
100%.
slipping that way. That's
Yes,
the same
absolutely,
way, and
100%. Wind.
you will not perceive a difference between Coriolis or wind correction. It will feel the same to you in an
Thank
aircraft.
you.
Thank
So
you.
no Coriolis, no
So no,
Coriolis.
yeah. So
No, it's there. It's just you're not going to know the difference.
so let me ask you a question. If you're on the equator, you agree as from a point in space that you're moving 1,034 miles per hour, correct?
I'd have to do the math, but that sounds about right.
Okay, yeah, or 24,900
It has
miles
to be
around. It spins around once in a day.
in
So
regards to space
yeah,
outside of the
yeah,
Earth's.
outside of
Yeah,
the Earth reference frame. So
right.
if you're at the North Pole, you're
Hmm.
not moving at all. You're just pirouetting like a ballerina.
Unless you're talking about the revolution of the Earth or the rotation. What am I
Oh, I'm
saying?
talking
Revolution
about
of the Earth around
your
the sun.
tangential speed. So
Right?
if you're on the equator and
Hmm.
your wings are pointed east and west,
Hmm.
you're moving sideways at 1,034 miles per hour
At the equator.
at the
That's
equator. Yeah. So if
probably
you're
about right.
if you, it is that's the Earth calculation. So
Okay.
if you're in northern Alaska, you're moving like 200 miles an hour because it's making a much smaller circle. It's not
Right.
making this big circle. It goes around
Right.
once a day. So you're moving, let's say, 200 miles an hour. So a helicopter takes off or an airplane.
Mhm.
It's got that tangential speed of 200 miles an hour. It could fly around in circles and land where it took off, no problem. But what if it flies to Ecuador and wants to land on a north-south running facing runway that's moving sideways at 1,030,000 miles plus per hour? How does it gain that sideways tangential speed to catch up to the Earth?
It already has it because it's in the atmosphere.
So, would you agree that
The air and the Earth are moving together.
the atmosphere, if the atmosphere is locked to the Earth, dynamically it blows left and right. No, somehow it's locked to the Earth, but we have summer breezes.
Right?
That comparing that to a flat stationary Earth
Hmm.
with dynamic winds, breezes, it would be the same. Would you agree with that? You would experience the same thing. A rotating Earth with a rotating atmosphere dynamically moving around summer breeze versus
Hmm.
flat Earth with an enclosed atmosphere dynamically blowing around. As a small micro observer of this giant system, you would experience the exact same thing. Would you agree with that?
The headings would be slightly different
I'm not
because
talking about that. I'm talking about your experience on flying from Alaska to Ecuador and landing. You
Mhm.
say the Earth is spinning, and as you go, you're locked into the atmosphere. But wouldn't it be the same experience on a flat enclosed Earth? Why would
like
your heading be any different anyway?
like I was saying, to your perception, the only thing that you would see different is your heading.
What would be different about the heading?
You would have to correct for Coriolis, which is what you would think is wind because
So,
you wouldn't know any
so you're
difference.
saying flying from Alaska to Australia, I mean to Ecuador, you have to correct for Coriolis, but the plane does it automatically. You don't have to nose down because the plane does it automatically. Versus on a flat Earth, when you fly from Alaska to Ecuador, you just fly.
Right. So you're going to see slightly different attitude indicator and slightly different heading in order to make both of those things happen.
Can I ask you a question, right? So, a hovering helicopter in your paradigm, in your mind, when it's hovering in one spot,
Mhm.
uh, it moves with the Earth and rotates, right? Is that your, if say if it was to hover, for the world records was 50 hours, okay?
Okay.
And the Earth didn't spin under it. It didn't. They landed back in the same spot. But are you saying if we were to see it from the outside observer in so-called space, would it be doing that motion, circular motion in space?
So the reason why it's hovering over the one spot is because it's hovering in the air that's going with the Earth.
Right. So it's actually turning, though. It's actually turning with the Earth.
Mm-hmm.
Okay. Well, that's a violation of the first law of thermodynamics because it's accelerating. In order to do a circular
Everything's
motion,
accelerating.
yeah, well, acceleration requires extra energy.
Mm-hmm.
So the higher up you go, you're saying the atmosphere moves in perfect lockstep as well at all altitudes. So
Well, it's
if
near
you go,
near
yeah,
perfect.
so if you go up more higher, where's this magical force coming from? Because the higher up you go on a globe,
The bigger circle.
the faster it has to go. Like a racetrack, if you're on the outside lane, you have to
Mm-hmm.
run faster to keep up,
Mm-hmm.
right? So the higher up you go on a globe,
Yeah.
the faster the wind has to travel. But
And that's what we see as
what's doing
pilots when we're flying at
but
high
what's doing that?
What do you see?
higher wind speeds at altitude. That's why it takes much longer to fly west than it does east.
Well, it depends on what altitude you're at because there's counter rotating winds depending on how high you are.
Yeah, but in the above, like North America, if you're going to fly like the North Atlantic tracks, the NATs, when you're going to Europe from, the east coast of America, or the Pacific tracks, which is, of course, the Alaska, Japan kind of routes. They are going to schedule what route to actually fly that day in order to make the gas the least amount because they're going to take advantage of those winds.
So if you look here, these white and pink winds, these are like 300-mile-an-hour winds that are circling. And then here they're going in the opposite direction. So we have counter rotating winds on the inner flat Earth and the outer flat Earth. So they take advantage of these. You know, the way they know this is they launch close to 1,000 balloons twice a day from all different spots across the Earth,
Mhm.
and they use ground antennas to track them and put it all in a supercomputer, and they can chart these winds. So this is how they know that airplanes where to fly. Like, hey, you ever notice when you leave a place, hey, you're 20 minutes, a half an hour late, but then you end up getting to your destination almost on time because they end up saying, hey, we're gonna put you in a tailwind, take you a little faster, and they try to make up all the times. They do a pretty good job. It's because of this.
No, they fly higher.
Depending on where the winds are, sometimes higher, and there's a better wind, a trade wind up there.
Mm-hmm.
But they tell us that these things are that all those balloons are tracked by satellites.
Actually, more accurately, I think what they're doing these days is they're using GPS and transmitters on the balloons to tell the satellites that are downloading the data from the balloons that are saying, I am at these coordinates and here is what the wind speed and everything is doing. It's also tracking it in real time. So then you're at this coordinate and then you're at this coordinate 1 second later and you're at this coordinate 5 minutes later. And it can tell you, where the balloon is going based upon those GPS satellites. Now, the one thing you're not taking into your calculation is all of the data that's coming from all of the aircraft that are airborne that have the, oh shoot, I just forgot the name of the system. It's the tracking of all the airlines. They funnel all their data, their wind data and everything into their models so that they know what the current winds and the real winds really are. So the forecast says it should be 150 miles an hour, and instead it's 160 miles an hour. And so that information goes into the weather models, and then they can recalculate where they should be putting the tracks the next time, or if they should be shifting the tracks or whatever, because gas is money, for an airline. So, and I've flown on both tracks. I've flown on the Atlantic tracks and the Pacific tracks.
So when you say GPS, you mean they're using satellites to track all of these balloons?
Yeah, in a way, that's mostly correct. The balloon is tracking its own position using the satellites.
So they're
So
using
just like
satellites.
you have a GPS, thing that says right now I am at these coordinates because this is receiving signals from all these satellites, and it triangulates and it says I'm right here, plus or minus an error bar, right? So
So we have all of these satellites that are orbiting in all these different directions, and they're all over the Earth. I mean, zoom in a little bit so you can see.
most of them are going 60 degrees north to 60 degrees south. That's primarily where they're at.
Right. And meanwhile, we're orbiting and spinning and whirling and twirling all in four different directions at once, all curved trajectories, not in straight lines, but somehow I guess gravity holds on to all of those satellites that makes them go exactly where they're supposed to go. And then they use how do they know where the balloons are? They use timing with signals.
The satellites generally don't track things. They're just giving off signals. They're saying, I'm
Okay,
here, the satellite saying, I'm here, this is the time, I'm here, this is the time.
right,
And there's a machine on the balloon that
right,
says, okay, I got satellite 1, satellite 2, satellite 3,
right.
and puts all those signals together and says, well, then I must be right here. And then
So
that becomes part of the data stream that is then sent to a different satellite that is like probably NOAA or oh shoot, the one that's in the center of the oceans. Yes, the oceanic ones. I can't remember the names of them. But anyways, they sit over the equator because that's the only place you can have geostationary. And they pick up those signals and they beam them back down to wherever their station is of the, where they're taking in the data and then feeding it into the models to do whatever they're doing with it.
where do the satellites get their power from? Because they're up there for quite some time, and is it solar panels? Is it nuclear? What are they doing?
Yes and yes, it depends. I mean, they all have a different way of doing it. Some of them are chemical, some are battery, most of them are solar panels. So yeah, they're going to be recharging all the time.
So what if we told you that all the balloons that they launch don't use satellites? They actually just use ground antennas.
That's possible, but
Okay. Well,
and I guess it's because they're usually not picked up. I mean, they're disposable, so maybe they're going to go cheap.
Angel.
Unless they're going to go pick up the
Yo,
balloons. I mean, the ones over the
well,
ocean.
No, they don't. Those they last for like 8 to 12 hours, and then
well,
they
one of our
nothing
buddies
around.
found one of our buddies, Geocentric, his name is on TikTok. He found one of these satellites and he linked it back to a website
Mhm.
that it was for GLONASS satellites, the Russian satellites. And
Mhm.
if you Google them and then hit images and look at what they are,
Mhm.
they depict them as these, typical satellites that are floating around in space. And they tell you that they're about 22,000 kilometers away,
Mhm.
but they're all on balloons. We've got the website now that shows us the tracking for them, and they're all on balloons.
Okay.
So why would they claim they're on satellites in space when it's proven that they're not? They didn't expect
Well,
us to be able to find it. So again, the globe model is lying, outright lying to us about what's above us. And you believe that the stars that we see are impossible distances away. Do you believe in scaling invariance? Like our sun, why does the sun look the same size as the moon?
chance.
Well, no, why? Why? It's bigger,
And
right?
it's not all the time.
Well,
That's why we have annular eclipses and total
that's
eclipses.
not what I'm saying. Well, let's just say approximately the size of the moon. Is that better?
Approximately. Okay.
Yeah. So why does the sun why does it appear approximately the size of the moon?
Chance.
No. You're not getting my point.
So it's 400 times
It's
further and
400 times
bigger.
further. It's
I
400
get
times
it.
bigger, and it's 400 times further by chance.
Know that the moon's orbit puts it at a visual distance to us on the surface to have the same angular distance or radius as the sun does, even though it's way bigger, but it's also way farther away. And it just happens by chance that the sun and the earth look to be about the same angular radius.
Yeah. So let me start again. Do you agree that they tell us that the sun is 400 times bigger than the moon?
No, it's
Uh,
way bigger than 400.
Okay, how many times bigger is it?
Holy cows. About 1,000 Jupiters will fit inside of the sun, and about 1,000 Earths will fit inside of Jupiter. Something like that. I mean, I'm pulling those ballpark numbers out. I
So,
remember
so
that.
you know what? Maybe I need to recheck my facts, but you agree. Let me back it down even simpler. The sun is bigger than the moon.
Way bigger.
Okay, so if the sun, let's just say, just for a number, is 1,000 times bigger than the moon, how do we get the sun and the moon to look the same size?
Because the sun is a
Approximately
lot farther away.
1,000 times farther.
Let me think about that for a second.
This is their claim.
If the radius of the sun is 1,000 times the radius of the moon,
I think it's 400 times. The sun is claimed to be 400 times.
Yeah.
Well, we know that that's not true because we have satellites around the sun.
We do?
Can tell you it's way bigger than that.
You do? You have satellites around the sun?
Well, NASA says they are. No, so if we want to go into that,
Yeah.
we actually agree that NASA lies a lot.
Yeah. So, my point is the sun looks the same size because it's significantly farther than the moon, correct?
Correct.
So if the sun, let's just pretend it's a mile over your head at noon, it would fill the entire sky because you'd be on a BB and the yoga ball would be a millimeter over your head. The yoga ball is the sun, right? So that's the scale we're talking, just approximately. If the sun was a mile over your head, would it fill your entire view of the sky?
Say that one more time.
If the sun was 1 mile over your head, the sun at 860,000 miles across,
right,
a mile over your head, and you looked up,
right,
you would only see the sun.
Probably.
Okay. Definitely, but we'll go with probably. That's fine.
Right.
So
you'd also be fried to a crisp.
I'm just talking scale here.
I know. We're doing thought experiments.
All right. So if we move the sun 93 million miles away, all of a sudden it becomes the size of a coin held at arm's length, just like we see it. Okay.
Yep.
So it got smaller. Why?
That's our visual
perspective. It's how perspective works.
Yeah.
So every time you double the distance of something, you realize it's half the height and half the width. So it would be a quarter of the size.
No, because size is just the radius or diameter, and you're only going to go with one dimension because it's round.
So it's half the size? Is that what you're saying?
I got to double check that. I'm pretty sure.
Double check it, but I'm going to go with half. It's a quarter, but I'm going to go with half just to give the benefit of the doubt. Mm-hmm. So at 93 million miles away, mm-hmm. It's the size of a coin. If I doubled it, it would be way small. It would be the size of a pencil eraser, maybe a little bigger. And then if I doubled it again, so now it's 4 times the distance. Mm-hmm. It's getting to be it's going to get pretty small. It's going to be, small, like a pencil eraser at arm's length away. And then if I doubled it again, so it's 8 times farther, it's now getting close to the size of like what Jupiter looks like when we see Jupiter in the sky. Would you agree with that?
That would be probably a good estimate.
Ballpark. Yeah, mm-hmm. Ballpark. So 8 times. So they tell us the sun is 8 light minutes away. We're going to change from miles to light distance. Mm-hmm. 8 light minutes, 8 times 8, 64. At a light hour away, it's like the size of Jupiter. At 2 light hours away, how small is it? It's getting close to looking like a distant star at that point, right?
Well, that's what it is. It's just a closer star.
So just help me out with the size here. The size. So if I made it 2 light hours away, 4 light hours away, 8 light hours away, 16 light hours away, mm-hmm. you actually, its angular size would become too small to see. So at a light day away, we'll just jump to 24 light hours away. At a light day away, you could not see the sun. Its angular size is too small for your eyes to see.
Well, our star is an average star, and the ones that we typically see are the huge ones.
Sure. So you agree that scaling invariance, the sun is X number of times farther than the moon, therefore it looks like it's the same size as the moon. If it's 400 times bigger than the moon and 400 times farther, it looks like it's the same size. You agree that works. We'll get those exact numbers. Will you agree at a light day away, It's not an opinion. You can go do the research, do the math, and find out the angular resolution limits of your eyes, and you'll realize that a light day away, you can't see the sun. Let's make it 2 light days away, just to give it the benefit of the doubt. At 2 light days away, you cannot see the sun. Now, can you see Polaris from Texas?
Yeah.
Of course. Naked eye. You can
At
see
night.
Polaris. Yeah, of course. But it's in the same spot, doesn't move.
Oh, yes, it does.
Well, it makes a tiny little circle, but it's in the same area of the sky. Okay. So Polaris is 46 times bigger than the sun. So at 2 light days away, if I made Polaris 92 light days away, that's double the distance. You could not see Polaris at 92 light days away. It's 3 months.
But you're also talking about different temperature stars. So the really, really bright stars are going to look, you're going to see them further.
I hear what you're saying. So at 3 light months away, Polaris is too small to see. But now you're saying the brightness, right? We'll get into the brightness in a second. At 2 light, they tell us Polaris is 433 light years away, not months away, years away. And if you do the inverse square law, every time you half the distance to a star, it's 4 times brighter, right? How bright is Polaris? You're talking like a 6 times brighter than the sun. If you're laughing because you never thought this through.
No, it's because we're talking about angular distances, and it doesn't go linear after a certain point.
It doesn't go linear. So at what
we can use it as an approximation other than to a certain point. But
at what point does a star stop getting dimmer and smaller as it's getting farther away?
It does, but not linearly.
But why would it do that? I don't get it.
That's just math. I mean, that's why when you asked me that before about angular distances and, that gets half, I'm like, I'd have to check to see where does it deviate from the linear relationship. So I'd have to double check. But it has to do with like the sine of theta is approximately theta if you're in radians. Oh, yeah. So there's an approximation that's being used here, and I don't know how effective it is when you get to a certain distance. But what's interesting is that if it is 433 light years away, that light left that star 433 years ago. So, it could have blown up sometime and we wouldn't know it for 433 years.
So when light travels, it doesn't spread out and get weaker. It just travels like a laser beam. Oh, it does.
It does, yeah.
So every time you double the distance to a light, it's a quarter of the brightness. At what point can't you not see it anymore?
It's a great question. It depends on a bunch of factors.
Well, let's pretend that Polaris is 10 billion times brighter than the sun. You know that at a light year, you wouldn't be able to see it?
I'd have to do the calculation.
You can do the calculations all you want. You can come up with ridiculous ideas on how bright it can be, but I don't know if anything could actually be brighter than the sun. I think the sun is the brightest thing in the sky. And these other stars, which you deny, the fact that we can zoom in on them and make them bigger, even though one of them is 50 trillion times farther, but we can still zoom it in to the same size. You're believing in all of this stuff because you were told. You've never been up there. You believe that gravity can hold air down, but you can't show me an example of air staying in an open container where the pressure outside of that container is even a fraction of a fraction less because it just equalizes always. All of the things that you're saying are faith-based and not scientific.
Absolutely not. Because when I was learning this stuff, I didn't just go, okay, and that was it. I calculated it myself. I looked at it. I made sure it all made sense because I had to be able to answer questions on a test or, whatever. So I had to understand it backwards and forwards as the theory goes. And so if it didn't make sense,
all right,
I would have known.
Do you agree that this ball has curvature?
Yeah.
Does the Earth have curvature?
Absolutely.
Can you see my mouth right now?
No.
Why not?
Because the Earth is blocking it.
The curvature of the Earth is blocking it.
Well, the Earth itself.
Yeah, well, the Earth itself. Yes, the Earth. It's hiding. It's hiding it. So on a curved Earth, do you know how far the horizon would be if you're standing at the edge of calm water on a clear day?
Mm-hmm.
How far?
I don't know the number, but I know where you're going.
It's 3 miles.
Okay.
So after 3 miles, you shouldn't be able to see the surface of the water if you're standing up and you're 6 feet tall. Is that correct?
Sounds about right. I'd have to calculate it.
Yeah. So what happens when you can see the water beyond that?
That's refraction.
Refraction. So can you show me an example of refraction? Now, I agree. Fraction is a real thing. Over distance, you become mirage, you become compressed, the light obfuscates gets absorbed into the atmosphere, and you can't see things. But can you show me any example of something hidden behind a physical object that refracts up?
Over the horizon radar?
Over the horizon radar.
Mm-hmm. Yeah, that's what your Navy people.
I'm talking about visually. I'm talking about visually seeing something. If Angel was outside and we're outside and he ducked behind a hill,
mm-hmm.
Could I see him? If
the conditions were right, yes.
Oh,
that's how you can see Chicago from the shore of Michigan.
Or would you also agree that we can, if the Earth was flat, we can see Chicago from the shore of Michigan?
Well, I understand that that's how you explain it, but I explain it using refraction. Because otherwise, in your theory, it would always be visible as the weather conditions were.
Absolutely not. I can see New York City. I can see underneath. I'm 25 miles from New York City. I can see underneath the Whitestone Bridge on some days. Other days, it's clear. I can't even see the city or the bridge.
Right.
And I shouldn't be able to see the top of the stanchions on that bridge, but I can see underneath the bridge. So the fraction, or is it just light obfuscation? Go ahead, Angels.
I was just going to say, you can't just cop out really by saying refraction, because refraction requires two different isotropic mediums. It's Snell's law, right? And our atmos is only one anisotropic medium. Yeah, I agree there's miraging and distortions, but that's not refraction. Refraction is when it bends at an angle. Yes.
No.
So basically,
that is one type of refraction. But if you've got minuscule refraction going over long distances, which is how you can see Chicago from Michigan's shoreline.
You're assuming that.
Wait, let me ask you. You didn't answer my question.
Conditions have to be just right to bend that light.
If the Earth was flat, we'd be able to see Chicago.
Say that again?
If the Earth was flat, we'd be able to see Chicago.
All the time.
Why all the time? On a clear day, yes.
Yeah.
Okay. We can.
Are you under the impression, Sandy, that a boat, when it goes away from you of the horizon, it's dipping behind the curvature of the Earth and you can't pull it back into view?
In the right conditions, correct.
That's been
most of the time correct. That's correct.
That's been falsified many times, even by myself. I've zoomed in onto the horizon and revealed boats again.
Yeah, refraction.
So you're claiming that the boats I saw, I didn't actually see them. They're actually behind the curve and they're refracting up around it.
The light from those objects is coming into your eyeball.
Yes.
And it was bent to your eyeball.
So there's hold on. There's different refraction on different days. Different atmospheric conditions cause different refraction, and so that refraction makes things stop exactly at your eye level. It never refracts them higher. It always makes them stop at your. It does. Okay.
Oh, so if you had a tower, and you went to the same spot, this tower is on the shore of Lake Michigan, and you're looking across at Chicago, and you go, I can't see Chicago today. Let me climb up one level. Can I see it? No. Let me climb up 2 levels. Can I see it? No. Let me climb up 3 levels. Oh, there it is. You could be able to do that.
Yeah.
Because on that particular day, the refraction was not enough to bring it to your eye at the level of you're standing at the waterline.
Or you're getting up high enough to see over what's blocking it from you, right? Water, waves, a marine layer becomes opaque. And if you get higher over that, you can see it, right? Here's a canal. In the winter, it's frozen. Ice freezes flat. Water freezes flat. Contained water lies flat. It freezes flat. We got the camera 6 inches off the horizon. Now we have these 4 lights out here, at 8 miles, 7 miles, 6 miles, and 5 miles. So the horizon should be 0.88 miles away. So we have two. I want to see what you think about this. We have two possibilities, right? So this one should be with like 50% refraction, which is crazy. I'm just giving it to you. 30 feet, 22, 15, and 9 feet below the curve. So these are all hidden. Like the bottom half of my face is hidden behind a curve. And at nighttime with no humidity, they're refracting up. So our options are 1A, Earth is flat and we're just looking at the lights. Or B, Earth is a globe at 0.88 miles away is the tangent of the Earth. And this one's refracting up that much. This one's refracting up that much. This one's refracting up more. And this one's refracting up more. None of them ever go higher. None of them ever go lower. They just stop magically at this tangent.
So actually they're refracting down.
These are refracting down.
So how would they be higher then?
Because, okay, if I can do this, let me see if I can do this with your model. Okay, so the light from one of these guys.
Let's go with this guy.
It can only go this direction because the Earth would be in the way otherwise. And so it would continue to go off into space. And so something has to pull it some way down to your eyeball.
What is that thing? That's something.
Refraction.
Refraction. It pulls. Refraction pulls. Refraction.
So we go back to Angel's idea where he said that you have to have two different mediums, right? Like a prism, right? Air to glass. And then you see it refract, it bends, right? You see it bend when it goes inside of this more.
It bends in a straight line.
Right.
Yeah, it bends in the straight line.
And then it goes out of the glass and it goes back out, up again, right? It goes away from the vertical in that glass.
Where's the second medium? Where's the second medium over the lake?
It goes from glass to air. So air to glass. Air to glass, it's going to go towards the vertical. And then when it goes from glass to air, it's going to go away from the vertical. That's because of the refractive index.
But where's the glass over the lake?
Okay, so now that we've got that established, right? We're okay with that. So far, we both agree. Okay.
Well, so not really. I don't...
Okay, well, get a prism or go find a video where it shows you the light going in.
No, I agree with that.
We agree with that, but we're on a lake with no humidity. It's nighttime.
Okay. Well, I go simple and then I get more complicated. Okay, so that's the simple one. We have all seen this in a science class. Now, what happens if there is no surface, but the air above is less dense than the air below, which is pretty much all the time, but it has to be just the right conditions, no wind, and a whole bunch of other things. And so now this light is going to be coming around the horizon. Sorry, I'm going to go use my analogy. And so it wants to go straight, but it hits this less dense air, and it's going to bend down.
So
you're basically saying
the tiniest amount every centimeter until you add it all up, and it makes a curve and brings it right to your eyeball on the lake.
So you're saying that those lights are basically holographic projections wrapping around a ball.
We've covered presupposed Earth radius, pressure without a container, angular resolution, perspective hijacking Earth curve. We've covered Boyle's law. We've covered diffraction limit. The one thing we haven't touched on was mirages. Give us the most ridiculous excuse of a mirage that you've had.
Well, the mirage is an interesting one because this is probably one of my favourite points to make as a flat earther, especially when someone says there's no proof of flat Earth. So I'll give you an example. We'll use Ranty and one of his images. So he has a picture of a clock tower at about 20 miles at Barrow-in-Furness, and it's just a picture of a clock. Now, as a flat earther, I look at this picture and say, clock at 20 miles. That's the end of my explanation. As a flat earther, I can make that statement. I'll say it again. Clock at 20 miles. Now, if you're a fundamentalist religious zealot, then that's not a clock at 20 miles. that would be a slightly looming, non-standard refraction hyena holographic projection of a clock from behind the reified edge of a sphere based on an R value and a begging the question proof of nothing perspective hijacking curve calculator to turn a clock which seems to be there into a clock which is not actually there. That's what you have to assert if you're a globehead. So it's not a clock, it's a holographic projection of a clock from behind the reified edge of an Earth curve based on a begging the question proof of nothing perspective hijacking curve calculator. As opposed to me, that's a globehead explanation. I say clock, 20 miles.
You're the man, Nath. You are the man. I love the way it's the way you taste, the way you say it. It's the way you say it. It's just you serve people like the Wimbledon final beautifully. It's poetry in motion. It genuinely is.
It is.
A soundbite classic.
Hey everybody, quick message that I'd like to share with all of you. Our lives are filled with toxins in our air, food, and even in the information we're taught. Avoiding them all is impossible, but helping your body detox doesn't have to be complicated. That's where Masterpiece comes in. Just 5 drops under your tongue twice a day, and that's it. Super easy, super simple, and it doesn't even taste bad. I've tried countless supplements, and while generally I'm pretty healthy, I didn't really feel much of an effect. But with Masterpiece, it delivered noticeable benefits. Check out the podcast I did with Terry from Masterpiece, linked below this video, or you can find links directly to Masterpiece on my website, flatearthdave.com, or in the shopping section on the app. The key to health is to detoxify. Now back to the show.
Well, they're really there, and the light is really hitting your eyeball.
But they're actually below the curve.
Correct.
How do you explain when we've done it over 20 miles on a lake where the sun is setting behind the person and the person on the other side of the lake has a mirror and is flashing the sun at them? Is that also wrapping around the ball, or are they actually seeing the flash in the mirror?
When we actually see a sunset, we're seeing the sun after it's already set.
I'm not talking about that.
For the
I'm
same
talking
reason.
about the sun is not set. It's above your head, behind you. I'm across the lake. I have a mirror and I'm flashing the sun, and you see that flash. How do you see that flash?
Same thing.
It's curving. So, or hold on, we're going to move on from this. That's fine, because we're not going to get anywhere with this.
There is actually a great YouTube video about a guy who used a fish tank and used
with the salt water, with the salt water, sugar water. And it goes down. It goes down.
Bent it down.
Go up. Yeah.
And that's because it was more dense on the bottom, less dense above. And so when he aimed it up, it hit the less dense stuff and it curved down.
But you understand that he's hitting it through glass. And also, we don't live in a sugar tank. We don't live in water. We're living in gas. You know what crepuscular rays are, Sandy? The rays that come out from the clouds?
Air is a fluid. It's just not as dense as water.
I agree. But can you find me a picture of crepuscular rays that are curving? Also, Sandy, you're saying the density gradient is what's causing this refraction. Do you agree that the density gradient is vertical, going up?
Usually.
Right. So if it's going up, there's no density gradient horizontally. Horizontally, there's actually no density gradient because it's vertical. So when we do observations looking horizontally, there's no density gradient.
Well, it's what I said. It was when the light is trying to get to you, right?
Yeah,
over here, around the curve.
So the light
has to go up into the less dense stuff that's above.
No, it doesn't. It stays in that same. You're saying it's curving in that same density. It's never going above the density that it's in. It's curving following the curve of the Earth, is what you're saying. Or we're going to move on. So that yours is we got refraction. We have this density gradient. We're seeing holographic projections.
Let me ask a question.
Hold on. Let me just finish my point. Okay. Or we just see it across the flat Earth. That's ours. Now, ours is just the simple one. All right, go ahead. Please ask.
Where does the density gradient come from?
Well, the Earth being a dynamic system, so basically all the Earth's gas is produced at surface level. So naturally, there's going to be more gas at surface level. The sun heats up the ground, which makes the ground hotter, which, like you said earlier, that excites the molecules and they move faster. And the Earth is a dynamic system. As you go up, it gets colder. Temperature has a direct correlation to pressure, right? As you go higher, you're going to get less pressure naturally because the temperature is decreasing, right? So, and we have different, all different kinds of gases, right, which move at different speeds, creating a gradient. I could show you that in a container. If you get a gas container and you heat up different portions of it, cool down other areas, make it a dynamic system, and we'll have a gradient inside.
Mm-hmm.
So,
okay, but something you just said was that the gas is created by the Earth?
Well, yeah, surface level. We don't have trees or oceans in the sky.
Okay.
so
Yeah, absolutely.
So it's a conversion, not a creation.
We're going to go with what you just said. The reason that we can see those lights is, so here's the surface of the water here. We have this oil rig here. We have another oil rig beyond it. What are Angel, what are the distances on these two? Do you remember?
So, yeah, the first one's closer is 6, and the one in distance is 10.1 miles.
Right. So at the height of the camera, the surface, the horizon, the physical edge of the curve should be in front of this first one. But not only can we see the water, we can see the water of the second one. We can see the water beyond the second one. So the horizon is far beyond it. So you believe, and as you said, you know, the light every centimeter is adjusting a micro. So the water here is refracting up, you know, whatever, a little bit, and a little more here, and a little more here, and a little more, and a little more, a little more, and all of it is refracting up exponentially, all to stop at the exact level to make us think we're looking across a level plane, but it's really a curved plane that's all refracting up at different amounts perfectly to give us the illusion of flatness. That's what you're saying.
Yes.
You said correct. Okay. That's
the globe theory.
Yeah.
So you're basically saying if a boat was to go away from you over that horizon, would it disappear at 3.4 miles in front of those oil rigs, or would it start disappearing behind them?
It depends on the conditions and whether or not that refraction situation is actually bringing the light to you exactly as you expect. If
The
that's
thing is, right?
Huh?
So the thing is, right? See how it's ramping up towards eye level? The water's ramping up, the sky ramps down. I mean, a hallway does the same thing, right? It just converges due to eyesight. So we claim our position is that the horizon's actually totally flat, and the convergence happens. The reason why we have that horizon line is due to eyesight and weather. The weather dictates how far away it'll be, right? Because the atmosphere becomes opaque over distance. Sometimes it'll be further out, sometimes it'll be closer.
Right.
But that's our position. Your position is that it should be 1.22 miles times the square root of the observer's height in feet, which is, for a 6-foot observer, the horizon should be 3 miles away, right? But it's not always 3 miles away. Sometimes it's 10 miles away, like we just showed. For a 1-foot observer, we've got it past 9.4 miles. It should be 1 mile.
Right. And
I comprehend your theory.
Right. And
I do
also,
comprehend your theory.
if we were like 100 feet in the air, we'd be the horizon should be farther out than 3 miles. But when we watch a boat go out, never does that boat refract up off the water, or it always stays on the water and it just keeps on going. If you're on a ball, everything should go down and away. The farther out you look, the farther down and away it should be. Agreed?
Yeah, you should start seeing the bottom of the boat disappear, and then the first level, and then the second, and eventually the mast will disappear.
Sure. So is this water flat out to this horizon?
Without refraction. I want to just put that caveat in for what I just said.
But if we're on a ball, it should be going down and away, right?
It is.
It's going down and away. So this water is going down and away. All right. So if I put two boats on here, this boat is closer, this boat is farther. This one is going down and away, right? This one is lower from my point of view than this one, but it appears to be ramping up higher. So you're saying that this water is curved down and away, but it's ramping up. No, I'm not up high. I'm at 6 feet here.
All right, that's an interesting.
So now I want you to watch carefully. Are hallways flat?
They're curved. I mean, slightly, very, very, very slightly.
Is this hallway flat?
I don't know.
Well,
Maybe.
it's a hallway. It's flat. This is perspective. And if I, it's a picture of a hallway, and if I merge it with the water, it's showing the exact same thing. But you're saying that the water is curved and the hallway is flat, but optically they do the exact same things. If I put the boats on the water and I take the water away, the boats are sitting on the floor in the hallway. So they're doing exactly what a flat hallway does, right? And then it gets worse. I'm going to put a sunset in here, right? The sun, this is just a random sunset I put on here. It follows the same line of perspective that the hallway follows, and it goes beyond the horizon and disappears. Mm-hmm. Here's another sunset. It's just going to go, it just follows that exact line.
It doesn't get smaller like that. It stays.
This is a sunset.
It gets slightly bigger.
This is a sunset. This is not, this is an actual sunset. Oh, it's not a sunset.
Well, I mean, I don't know what that is, if that's a computer simulation, but whenever
it's not a sunset. It's not a
it doesn't get smaller like that.
It does. I've measured it. I've measured it with the solar filter as well. It absolutely does get smaller.
Yeah, but sometimes it doesn't look like it gets smaller. Sandy, you ever go out and watch moonrise? We just had a full moon the other day. It was huge, right? You take a picture of it. You're like, look at the picture and like, that's not what I'm seeing. It's tiny in the picture. Mm-hmm. It's the way our brain processes things that are close to the horizon. We see them bigger. This is going to sound crazy. It's not going to fit into your scientific knowledge. The next time you see a giant moonrise, turn around backwards and look at the moon upside down through your legs, and it'll look tiny. Sounds crazy, but do it. And
well, I'll try it. Like I said, I'm a pure scientist. I'll do any experiment.
And then you'll have to understand how that happens. So I wanted to show you where is it?
I could show her my.
Can I ask one question?
Go ahead. And then Angel, you show.
Okay. How does flat Earth theory explain how Chicago was photographed upside down from the shore of Lake Michigan?
Yeah, it's a superior mirage. That's actually a superior mirage. So that's funny because that's what they were claiming, the one that Joshua Nowicki took. That was that you're claiming is refraction. But refraction actually looks distorted and upside down usually. So yeah, absolutely. It's just a temperature inversion.
So
that's refraction. That's what a temperature inversion does, is refraction.
Yeah, right. So the image of Chicago that Joshua and Nowicki took that wasn't upside down or distorted, you're saying that that's wrapping around the ball.
And not only that, but the light from the top of the buildings was just refracted more than the light from the bottom of the buildings.
All the Earth is just flat and we're seeing it. Right? All the Earth is just flat and we're seeing the buildings across the water.
Upside down.
No. Well, during the temperature version, maybe, but not otherwise. It wasn't just when it's not distorted. We're just seeing it.
Here's that famous picture Joshua Nowicki took, and here is a time lapse. Now, right here, just notice this building. It's not going to move, and this is over 18 hours, I believe. And we have different weather coming in, different temperatures coming in, and the buildings aren't moving. They're not moving. They're just staying there. They're just not moving at all. And so what happened to refraction? This is just what we see. That was the whole time lapse. It's not changing. It should change. And
it will if you do another day when refraction changes.
Well,
you'll see it disappear.
The day that we did an 18-hour time lapse, none of the buildings moved, but other days it will move. Mm-hmm.
Yeah. Well,
okay.
That was just a really cool.
All right. So how about this
coincidence?
Here's a day with refraction changing. Now we can see the beach here, and we don't really see the buildings, but now the beach is disappearing. The buildings are appearing. It's going up and down, right? What's going on here?
It's not the curvature getting in the way.
Is the curvature changing, or are we just having atmospheric conditions over a flat lake?
It's changing refraction.
It's changing refraction.
Mhm.
So we
Welcome to
can
flutter.
see things. Is anything from behind this mountain refracting up over it, like popping up?
I can't tell what's behind it, if it's a mountain or if it's a
Well,
water or what that is.
no, that is a mountain. But what my
Okay.
point is, you can try, but you'll never find anywhere where something hidden behind a solid object. Like if we're in a field, let's say we're on the salt flats, right? And we're 100 yards apart, we can see each other. If I put a 10-foot brick wall in between us, we can't see each other. Agreed?
Probably.
Probably.
Well, I can't,
So we're on a
So far, I'm listening.
we're on a football field.
Remember, I can't give you 100%. I'm a pure scientist. Keep going.
We're on a football field.
Okay.
And we're both on the 25-yard line, opposite 25-yard lines, and
Okay.
put a 10-foot brick wall on the 50-yard line. Can we see each other?
Probably not.
Okay. And now let's extend that football field to hundreds of miles.
Mm-hmm.
Flat or globe? How far back do we have to go before we can see each other?
Flat is an easier calculation.
But we can, is what you're going to say.
I'm trying to think.
At some
can
point
do that.
in your theory, we're going to pop up over that.
I'm trying to do. I'm
Yeah.
doing the thought experiment as we're speaking here. So
Right. So the answer is in your world, I can tell you that
should not in a flat Earth. You should not ever see each other.
Wait, well, how come I won't refract up over it?
Well, I didn't think there was refraction in your flat Earth theory.
Well, why wouldn't there be? If
Of course there is.
Yeah, there is refraction. It's just not of things that are in line of sight. Anything in line of sight, there is a refraction. But once it's out of line of sight, here we are in Illusia, France, and we're looking out here, and Mount Canigou is out here, and you can't see it because it's 175 miles away. Using the Earth curve calculator from the altitude that we're looking from and the distance, the top of Mount Canigou should be over a half a mile below the curve.
Okay.
Right? So you can't see it. Well, the sun moves in between the tropics, right? You know, it moves on a flat Earth, right? It moves between Cancer and Capricorn. And twice a year, it lines up with the viewer and Mount Canigou. And on those days, let me just speed this up a little bit, the sun will move beyond it, and all of a sudden, you can see it. Here it is. The top of this mountain, the highest point right here, should be a half a mile below the curve. But there it is. Twice a year, you can see it. Now, your answer is, well, the sun already set. The mountain is below the curve, and the sun is refracting up. And somehow the dark mountain is refracting up and blocking the sun's refraction. That's your answer, whether you know it or not. Or the sun is just flatter than the mountain, and it's flat, and it's just due to perspective. It's backlighting it.
Mm-hmm. Well, it doesn't matter if there's a mountain at the horizon or if the horizon's just flat. It's still in the way.
How if the mountain is below the curve? So let's pretend that
I get it.
Let's pretend this is a mountain.
Mm-hmm.
It's below the curve.
Right.
How is me putting a light back here going to make this block that light?
It's probably not cause and effect. It happens to create the proper refraction to bring both objects to your eye.
It happens like this is on a date that it happens.
Happens twice.
So are you telling me on
a
specific this specific date, these refractive conditions occur every single day, every single time? The other thing you got to be aware of is
there's never been an exception.
No, a cloudy day.
No.
Yeah, on those days, if it's really foggy, you can't see it. But that's just visibility.
Okay.
But the mountain is being backlit. We're seeing the silhouette of the mountain. Now, you agree that refraction, the simple definition, is the bending of light, okay? But you can't bend the absence of light, yet we're seeing the backlit
We're seeing the
mountain.
The refracted sun, or the actual sun, being blocked by something physical. That something physical is below the curve, and it has no light on it. How is it refracting up and blocking a light?
It's flat.
I keep saying refraction. I mean, it doesn't matter.
Well,
How can you see the water over the curve of the Earth?
Or it's
That's what you
flat.
were
You
showing. That's
can't.
what you were showing with the oil rigs.
No, I was showing you that we can see the water because the Earth is flat. You can't see it over the curve of the Earth if the Earth is a ball. It's flat. You say that airplanes adjust for the curve of the Earth. Do submarines adjust for the curve of the Earth also?
They have to,
They do.
because the water is curved.
well, do you know that actually half the sea floor, more than half of it, is claimed to be flat? It's abyssal plains.
Well, but then there's a lot of tectonic faults and volcanoes and seamounts and lots of other
So I
stuff
just,
too. But
you know,
yeah.
I just quickly want to show you my own personal video I took of that boat, right?
Mhm.
Because this shows what Dave was showing you earlier with the ramping up of the hallway, right?
Mhm.
So I went out there. I couldn't see the boat with my naked eye or the camera, but I zoom in and I increase angular resolution to the horizon.
Mhm.
And then it re-reveals this buoy in the boat in the distance.
Mhm.
Right now, is your claim that that boat is actually below the curve?
If it's more than a distance away, yes, it has to be.
Wow. But okay, so this is the other thing, right? See this buoy in the foreground?
Mhm.
It appears lower than the boat in the distance, but when you actually look down at a slope, the things in the distance will appear lower than the things in the foreground. So that's why in that hallway demonstration, the hallway floor is flat, but it just appears to ramp up, right? So the things in the distance appear higher, but they're actually all on the same level. And you see it here, right? You see
Yeah,
these
but that's
boats are
where you're
ramping up.
standing. Yeah, you're standing higher, so that's going to cause a different
Yeah.
perspective.
Yeah, absolutely. But
If you laid down on a
it's
Home
not
Depot
Earth
floor and you looked across the Home Depot and you had small objects laying all down the aisle, you wouldn't be able to see them all. But if you lifted your head up, you'd be able to see them all, right? Even though the wall is perfectly flat, there's no atmosphere issues, right? Here we have water. They say this is the Earth curve. This is just the limit of our vision, or what I call our horizontal eye zone. But if we zoom in with today's consumer optics, we can zoom into this line, and all of a sudden we see these are dolphins that are far beyond that line. They're jumping out of the water. So are they jumping over the curve of the Earth? Are they refracting up? Or is this just where we can't resolve the surface of the water anymore? You can see the water that when they splash, that they're crashing into this water out here,
Mhm.
right? So you think that these dolphins are refracting up over the Earth curve when in fact it's just a limitation of our vision. There
I
is no
understand that's your
curvature.
theory. Yes,
Okay,
I understand that's your theory. Mhm.
got it. Any other things with the Earth and not the sky that make you that you think prove the Earth is a globe?
I've been to Antarctica.
Okay.
that doesn't prove a globe, but okay.
Yeah, so I have good friends that have been stationed at the South Pole Station for an entire year, and
Okay.
they have 6 months of day and 6 months of night.
Have they ever filmed the sun circling around for 24 hours? Do you have
More
that
than
video? Can we see it?
And they've also done the stars going around them, because the pole, of course, the Earth is turning, and so the stars are just looking like they're going through space, like little star trails. You'd see the same thing but different stars if you did it at the North Pole, which is just an iceberg.
So let me ask you a question. Before we were talking about Polaris, and I said Polaris doesn't move, and then you're like, yes, it does, right?
All the stars do.
Well, Polaris stays where it is and makes a tiny little circle. Would you agree with that?
I believe Polaris is part of the Milky Way, and so it does have an actual velocity with respect to the Earth.
But we see it in the same spot all the time.
Only in our lifetime.
only in our lifetime, but in a certain amount of time, it will be out of there, right?
It's not going to be the North Star. No, it has never been the North Star always because
So you're telling us that Polaris, which means pole star, was not our pole star.
it hasn't been throughout the
So
history of the planet. No.
why does in the Giza pyramid, why is there a shaft that points right at Polaris?
It actually points at where Polaris was when the pyramid was built.
You mean where the North Star was when Polaris was built? You mean Thuban, and now it's pointing towards Polaris because the Earth has moved. Is that what you're trying to say?
Well, it's like a spinning top that's starting to get ready to fall, but
So
it doesn't.
when the pyramid was built,
Mhm.
Polaris was in the line, then it moved out of line, and now it's back in line. Or what I think you're trying to say is they built it pointing north, and there was another star there. I believe it was called Thuban, and now it points to Polaris 2,000 years later, whatever it is. Right?
It could be.
That's
Yeah,
what you're.
I haven't.
That's what you're trying to say. So
I haven't done that exact
while we're
research,
moving, while we're moving 4.5 billion miles a year, never to return to where we were before, moving 186 million miles from one side of the sun to the other, somehow Polaris stays in line. And your answer is it's so far away that there's no parallax. Is that correct?
probably.
Okay.
I would have to double check, but that sounds about right.
Okay.
The parallax is there. It's just, can we detect it?
It's so far away that 4.5 billion miles a year is over hundreds of years or thousands of years isn't enough to make parallax. Okay, an argument. It's a wild argument.
Right.
But what does matter is the wobble of the Earth, because our pole is wobbling 1 degree every 76 years. Right? Our pole
Allegedly.
We're actually tracking a circle in space.
Yeah. So if this is our pole,
wobble.
it's doing a 26,000 year wobble. Okay. So that's 1 degree every 76 years. 1 degree is 2 to 3 full moon widths in the sky.
Okay.
Right. So the Georgia Guidestones had this little hole in it. And that hole, when you look through Polaris is there, and you could do a time lapse, and it shows you the Polaris stays in that little straw size hole.
Mm-hmm.
Right. The Georgia Guidestones were built in 1981, and over 40 years later, that's a half a degree tilt. That's at least a moon width to a moon width and a half that Polaris should have been out of that hole. That would have been far out of that hole. But we went there, and Polaris is right in the center of that hole.
Yeah, I could show you time lapse, real time lapse from there.
Hold on, before you show that, and so we made a video about it. It started going viral that this is rock solid proof, and then a couple weeks later, a terrorist blew up the Georgia Guidestones. Bulldozers were there 3 hours later, took the entire thing away, stole the time capsule, and there was no investigation. Do you find that weird?
I do find that weird, but
Okay.
I don't think it's for that particular reason. I think there was something else going on.
What?
I don't know.
So
I'm not an insider.
Right. So you suspect there's something else going on. You have no idea what it is. We gave you a darn good reason, which is called rock solid proof that the Earth is not wobbling. And that can't be the reason. There has to be some other unknown reason.
Well, I know you said was it 72 years for 1 degree?
No. It's 76 years. Yes. Close. Yeah.
All right. Yeah. Because it's not 26,000 exactly. I just did a quick math.
It's 76 years. So it was up for over 40 years. Polaris was still in the hole. It's actually rock solid proof that it was, and it's still there. And
how big is the hole? Would be my
first. The hole
first
is really small. It's like the size of a straw.
Okay.
Right. And the same thing here at Coral Castle. Right. Edward Lee Scallon built this, and there's this little target up here, and from this little cornerstone, there's a little hole you look through, and Polaris will be in each season. It'll be actually it goes here. Winter, spring, summer, fall, whatever, and it does this, and it's been there for I don't know how long it's been up. So my prediction is something's going to happen, and this is going to get shut down.
Okay, we'll find out.
again, everything, all the stuff that you are claiming that the refraction on the ice and everything, you have all of these excuses. I'm just going to call them excuses, no offense. And we just no, because it's flat, because it's there, because we see it, because it's not wobbling, right? And so those, it's very, very simple. Angel, show what you wanted to show her.
Georgia Guidestones, I think. Yeah.
Yeah. You want to show her time lapse.
Yeah, so this is a real time lapse that our buddy Nathan Thompson took. And you'll notice that the other thing you got to be aware of with these time lapses is the star trails are super clean cut, crisp circles. Now, if you're spinning on an axis, orbiting the sun, moving through the Milky Way, and that Milky Way is moving through the entire universe, how in the heck do we get perfect, clean-cut circles that do not intersect?
And our spin is the slowest speed of all. Doesn't even come close to the others. Do you know how fast we're orbiting the sun?
Well, let me answer Angel's question, which is the stars that we can see with our naked eye are really close to us, which means that they're orbiting at almost the same velocity as we are through the Milky Way.
Wait a minute. The stars that we can see with our naked eye, we can see Polaris. It's 344 light years away. That's close.
That's pretty close.
Wait, but the stars in your paradigm, aren't moving with the Earth.
Right. And you're forgetting the fact that we've debunked being able to see Polaris at 344 light years away. It's only 46 times bigger than our sun, and it's 344 light years away versus 8 light minutes.
Right.
8 light minutes times 46.
I told you that the linear relationship for angular distance doesn't work. So I would have to actually go back to the calculus and see what it's supposed to be.
Okay, you can do that. Any other thing?
Do you have any other proofs of the globes?
Yeah.
Well, like I said, I'm going to do the electrostatic experiment I told you about as soon as I can find time.
Have you ever seen when lightning strikes the ground really hard next to somebody, they go flying in the air? Have you ever seen that? Lightning strikes and they go flying in the air. They literally get ejected from the ground. Have you ever seen that? You can look it up if you haven't seen it.
No.
It's what is the gravitational explanation for that?
Probably a rebound. It's probably going to be a huge amount of charge on the one versus the other, but I don't know.
Very good. That's very, very good. It actually reverses the polarity of the Earth, ejects you from it, then you're in the air, positively charged again, and you come
that very
down.
Local area where it was possibly. I don't know. Okay. It could also be that all those electrons running through that poor person supercharged all their muscles and made them all, because they just go
jump.
You make you jump like you can never jump before.
Yeah, I don't think that. I like your first one better. Your first one actually makes more sense, and the first one is my theory on what it is.
Let's look up Barnard's star.
That's the one that moves, right? Yeah, there are some stars that move. What are they? The question is, we talked about
they're not stuck to a firmament.
I'm not saying that they are. I'm saying that the stars that we see are cannot be. I don't know what stars are, right? They cannot be gas in a space vacuum. And here's another thing: we launched a balloon in Arizona, somewhere at nighttime, and they had the 4K cameras looking up. And before we launched it, clear night, you can see the stars, you can see the Milky Way. So as you go up higher and higher, the viewing should only get better and better, right?
Generally.
Right. Mm-hmm. By the time it hit 60, 80, 90,000 feet, all the stars were gone.
That's interesting because the Hubble telescope can see zillions of stars.
Zillions and zillions. The Hubble telescope. Have you ever seen the Hubble telescope in space?
Nope. But I've seen
a picture. You've seen a picture.
Mm-hmm.
Well, we can talk about that next. So they told us just recently that the Hubble saw.
Actually, no, I have, because, well, not me, not me visually, but the astronauts doing the servicing of it when it had its myopia or whatever, and they had to have glasses.
I remember.
Remember that?
That was nail biting, movie. They saw the Hubble did a long photograph of something of a galaxy 13.4 billion light years away. 13.4 billion light years, right? You know when they
that
do
one I don't believe.
Okay, well, this is so NASA is not a credible source. Okay, so a lot of the stuff you quoted us today came from NASA. So your source is not credible.
But you can actually see Barnard's star. It's close enough that you can see it.
So you can see it. It's close. Welcome to flat Earth.
Not that far away.
It's not that far away. You can see it. It's not gas billions of light years away. It's not gas in a space vacuum, right? So you don't see this. Just showing you, 1 light year is 5.8 trillion miles away. The moon's 237,000 miles away. We said, why don't they zoom in and show us the stuff on the moon? That's 24.8 million times farther 1 light year, right? So we have to take that 1 light year and multiply it times 13.4 billion to say what they saw. This is just nonsense. You're a numbers person. So now basically NASA's not credible. And anything, your distances to stars, everything you're saying, satellites, it all comes from NASA. So you're using a non-credible source.
Doesn't all come from NASA.
Well, where'd you get the radius
From a
value?
huge number of astrophysicists all around the world.
Where'd you get the radius of the Earth from?
Well, depends. You can get from a whole bunch of places.
According to your paradigm, it was Eratosthenes who measured it with 2 sticks and shadows. Right? He had to assume that the sun was really far away. He had to assume the Earth was even a globe to begin with. And then he did a bunch of math and then got a ball as a circumference, right? But we don't observe parallel rays. We observe crepuscular rays that diverge right out of the clouds.
Yeah, we never see this. We never see this.
And if you get a local light source and put 2 sticks on a flat plane, you get no shadow and you get a shadow. So that's not proof of anything.
Right.
And also we've just debunked the radius value over and over with our observations. I think with the ORIG one we showed you, the Earth would have to be the orbital path of the moon. That's how big the Earth would have to be if it was still a globe, and it can't still be a globe because the whole heliocentric paradigm falls apart if the radius value is wrong. Because then the distance of the sun is wrong.
It goes back to the angular distance thing that we just talked about that I'm pretty sure we're not doing right here.
Well, if we see too far, if the horizon is in fact too far, it's not the Earth getting bigger, right? The Earth's not getting bigger and smaller. So basically, again, our position is just that it's flat, and the weather dictates how far away it'll be.
You said you saw the ISS, so you think that there's people on the ISS?
I don't know if there are any more, but
you think that there were people on the ISS?
But
if we catch them faking, gravity, 0G on the ISS, is that enough to discredit it, or using green screens, or using augmented reality, or zero?
All we can say is for each of those specific instances, and I have seen the green screen, what do you call it? It's like on the control screens, at like
we've seen that. We've seen that.
Yeah, we've seen that. We've seen.
Have you seen bubbles in space? Have you seen the bubbles in space on the live feeds from the outside?
You've seen people fade in out of nowhere on live streams.
And you see the ones where they're supposedly on either the shuttle or the space station, and you can see the wires holding them.
Yeah. Is that a problem?
They're probably on the Vomit Comet instead. And
right. Have you seen this one? This is from a live feed.
Yeah,
we have a stream. We have a seam across here. So when people say, "Look, there's proof of the Earth," where's this seam come from?
Mhm. No, I get
This is
it.
from a live feed.
But all I can say is that's fake, and that one video is fake. Does that say all videos are fake? No, I have to
Why
do
would they?
each
Why
one
would they
individually.
fake anything? If they were in space, why would they fake anything?
Unless something's happened and they're not telling us.
So
And they had
something
to
that you don't
abandon us.
know,
I
again,
don't know.
you're theorizing on things that you don't know, speculating to support your globe religion.
The ISS is in the second law of thermodynamics violation. Have you ever seen that image, the pale blue dot, Sandy?
Yeah, from Carl Sagan.
Well, it's a picture of Earth allegedly from like billions of miles away, and it's a little dot on the Earth, and then there's an infinite void.
You're talking about the same thing. Yeah.
Right. So, okay. So if we get a gas pressure on one chamber, and then a valve, and then a vacuum, every time we open the valve, the gas pressure will rush to the vacuum. Now, that little infinitesimal small dot of an Earth with its tiny little bit of gas around it, that gas would just go, boop, be lost into the infinite vacuum, and you'd have no air to breathe.
No.
Absolutely.
Only in a flat Earth with no gravity and no dome. Then it would do that. But if you have gravity in a round globe, gravity will hold the atmosphere in.
But gravity's not gravity doesn't affect gases. Gases move randomly in all directions.
Sandy, you said that before. That is your theory, but we can do an experiment, right? I got my box of air at the same pressure as the room, and then I lower the pressure in the room by the most infinitesimal amount, and the air in that box will lower at that same amount. The entire thing. So gravity is not holding it in. And as I pull the air out of the room, the air comes right out of the box also, whether the hole's on the side, the top, the bottom, doesn't matter. Because gravity does not hold air down. I can disprove gravity with a straw. I can put it in my mouth, and with the weak, faint, low pressure system of my mouth and lungs, I could pull air and water up and away from gravity. Easy.
Gravity's not that strong.
Gravity's not that strong. It's not holding air down.
Sure it is.
Not, well, that's your belief.
But
can you prove it?
It's your theory. So the theory, you need an experiment to support it. I'll do an experiment. I got my fish tank, tops off of it. I lower the pressure in the room a little bit. The pressure in the fish tank lowers also. Gravity should hold it down in your theory. The air should not leave the fish tank.
Well, it depends on what temperature we're talking about. Like I said, we got to go to absolute zero to see the effects of gravity, or very close.
No, yeah, I mean, you're assuming that, but you can't show us an experiment of someone holding gas down with gravity. You can only say that. You can only beg the question. You can only look to the sky and say, oh, well, look, a gas pressure gradient is there. It exists. Therefore, gravity is creating it. But I can prove to you in a container why we have the gas pressure gradient using temperature variations and making a dynamic system. And then I could go outside and say, oh, look, a gas pressure gradient, therefore it's contained. I can prove mine. But no one's ever going to be able to prove it with gravity. Right. They can just say it.
And you want to believe NASA, but NASA tells us the sun loses 4 million tons of mass every second for billions of years. Andromeda is getting closer to us by 110 kilometers per second. 60,000 new stars are born every second, and 120 new black holes are formed every second. Is that coming from a credible source?
So here's the problem.
Yeah.
Some of the stuff that NASA says is true.
Like what?
And some of it that they say is false. And we have no freaking clue which ones are which.
So why would you believe liars?
Why would you believe any of it then?
I don't generally. That's why I said I've seen the space station. I've seen Starlink satellites. I've seen meteors. I've seen eclipses. This is stuff I can do with my eyes.
Okay. So you've seen go ahead. You start.
I was just going to say, the fact that you can even see Starlink disproves how far away it is. If we put a school bus 300 miles away and you have direct line of sight to the school bus, are you going to see it 300 miles away?
If you shine a really bright light on it, you will.
Nope. Its angular size is far too small for you to see.
if you use your approximation of angular distance, yes.
Right. Well, the Starlink satellites are smaller than a school bus, allegedly, and we can see them from 300 miles away with our naked eye.
Mhm.
That's impossible. You wouldn't be able to see them.
Yeah. And do you remember, have you ever seen the line of Starlinks going by in the sky? I have. You've seen them?
Yep.
How long ago?
Last time I looked was, oh my gosh, years ago now.
Yeah, years ago. So when Starlink first started going up, everybody was reporting seeing these, and I didn't believe it at first. I'm like, get out of here, really? Right? And then I saw it myself, and I'm like, whoa, right? But many people report before that line comes through, they hear a jet fighter ahead of it, and they hear a jet fighter behind it. I don't know. They're just hearing jet fighters. It's weird that like military planes are always in earshot of when we see these things go by. Now, since then, they've put up thousands and thousands. Do you know the number, Angels? How many they've put up since then?
A lot.
Yeah.
I'll agree with you. They say it's a lot.
But now nobody sees them anymore. Everyone should be seeing them every night. But now they don't see them anymore because this is a magic show. This is a parlor trick to make people believe that they can see something smaller than a jet engine. So the Starlink satellites are way smaller than a 747 engine, but we'll just say they're the same size, right? A 747 engine at cruising altitude, 7 miles, you can't see the engine. At double that height, 14 miles, you can't see the 747. It's too small to see. But these Starlink satellites, if they're directly over your head, that's the closest they could ever be. That's 350 miles. And we can see them. And we can hear jet planes in front and behind. You're being fooled. That's it. You're just being fooled. And the question is
your theory.
Well, that's my theory. And your theory is that you can see something smaller than a jet engine at 350 miles away.
With a bright light on it.
That's your theory.
Mm-hmm.
Do you ever do the math on that? What kind of bright light? How bright would that light have to be?
Probably the sun.
So the sun, so the Starlink satellites are reflecting the sun as bright as the sun. And they're reflecting on, they're only 350 miles up. So somehow the sun is lighting them up perfectly.
Mm-hmm.
That should flicker. Like usually when you see a plane in the distance and it flies by, sometimes you see that light flicker, right?
Right.
It doesn't always stay illuminated.
If it's reflecting the sun, somebody a couple miles away or 100 yards away shouldn't be able to see that same reflection. If you guys were on the beach 20 feet apart and I flashed a mirror at you, Sandy, Angels wouldn't see it, and vice versa, right? So these are somehow reflecting and everyone can see them. And now that there's thousands more, nobody's seeing them anymore. What happened to them? Did they become dirty, less reflective? And here's a funny thing. An argument that you should come up with is, well, it works. Service works. I've used Starlink service. So have I. It's amazing. It's great. Okay. But Starlink service, if you look at a Starlink receiver, it's the same equipment that the soldiers used in the Vietnam War when they were using AWACS planes to relay their signals. It's the same equipment. Starlink is just using airplanes to relay signals. Airplanes everywhere. They're everywhere in the sky. So that's all Starlink is. And those airplanes are only 7, 10, 20, 30 miles away. And they have power source. They can be serviced daily. They know where they are. And anytime there's a space where there's not, they can always send an AWACS, a drone or whatever to fill that space. If there's weather, they can put some high flying military planes above it. Starlink service is amazing. It's not tin boxes using solar panels falling around our Earth, maintaining their positions everywhere. They're just airplanes with Starlink service on it. I asked AI about this, and AI said that putting Starlink satellite communication equipment on airplanes is a far more robust system than the theorized Starlink orbiting satellites.
That's an interesting theory.
Okay. It's a good one, though. Versus It's
Well,
impossible
there is
to
a way.
find.
There is a way to test it.
Yeah.
We would need to be able to see Starlink again. Someone somewhere would have to be able to find it.
Okay.
And they could, especially if they see it like, straight ahead, and then hit a stopwatch and then watch it go through space. And then when it gets to the horizon, so in other words, it's gone 90
you mean see
degrees in
these
their
guys?
field of view, and then click. How long did it take? And we could calculate how fast it's going.
So funny you should mention that. We have a couple people. One guy, he lives, I forget what island it was. He lives somewhere in the South Pacific on an island, and he has Starlink service. And he says that he's like a military guy, and he tracks all of the airplanes in the sky all the time. And he says whenever the last airplane leaves his area, his Starlink service dies. Weird. Just a coincidence, maybe.
It's a data point. I mean, that's the thing, right? We add
it's
up
a data point. I'm with you. I'm just giving you data points. And then you said you've seen the ISS. I've seen it. I use my tracker. It's going to show up there right on time. There it is on the horizon. And it went right over my head. So when it's over my head, it's 250 miles away. It's traveling how fast?
Well, we could do the math.
17,500 miles an hour. Okay. 17,500 miles an hour. And I watched it for 8 more minutes. I could still see it. It never got any smaller. I saw it for 8 more minutes. 17,500 miles an hour. Someone do the math. It's like 3,000 miles it went. I'm looking at something the size of a 747, 3,000 miles away, and I could still see it. It's still lit up like the sun. It never flickered out. From horizon to horizon, it was the same brightness and same size. Does that make any sense to you? Does it?
Well, you said your eyes adjust, so maybe that's all that happened.
So my eyes adjusted to seeing something the size of a 747, 3,000 miles away. I am able to see it. And somehow it kept a perfect angle to the sun where that sun was reflecting into my eyes.
It was never 3,000 miles away.
Angel, go ahead. I'm going to just do a quick calculation.
So when it's directly overhead, 250 miles, you're only seeing a small part of its orbit by the time it reaches your horizon. And so it's only going to be like, I'm going to guess, I don't know, 300 miles maybe at the horizon in its orbit.
Do you reckon you could see a football field from
you're right. It's only
miles away?
2,333 miles. So I saw it. It went over 2,000 miles farther. It never got smaller. It never changed its reflective properties. And I could still see it. Could I see a 747 to 2,000 miles away?
Like I said, that approximation you're using for angular distance isn't working.
Why not?
Well, if you're actually on a global Earth,
we're not, though.
Then
so we're not.
By the time
you're right.
By
it
the time
it
gets to over your horizon, you've only seen a small part of its orbit, and so it's not changed much than the 250.
When it's over my head, that's the closest it's going to be from me.
250 miles, like you said, probably.
And if it's moving at 17,500 miles an hour away from me, it's moving. It's
not away from you. It's moving in parallel or perpendicular to you. It's in orbit.
Yeah, but it's still moving away. Like when a plane flies away from you.
Yeah, it's still moving away from me.
It's only a small amount of its velocity is actually moving away from you. The rest of it's in its orbit compared to you.
That's just incorrect. So we can agree to disagree on that one. Where we're going? We had another topic. We had another topic.
Yeah, look, with the Earth's motion, okay. If the Earth were to speed up and slow down, would that be a problem? Would you feel that? Do you think?
No, it does speed up and slow down.
Yeah, I know, and you don't feel it, and you can't measure it
because it's really, really slow and small.
So also turning is.
But we do see something. What does flat Earth theory say about what we see of the moon's surface?
We don't make a positive claim. We don't know what it is.
Oh,
you guys make it.
Okay.
No.
All right. Anyone that has binoculars or a telescope
I've looked at it many times.
can see more than 50% of the surface of the moon over a orbit, let's say.
Okay. I think the moon's a sphere, if you ask me. The other people don't.
It's close.
I think it's a disk. I don't even think it's a sphere.
Okay.
That's why we only see one side of it, is because there's only one side of it to see.
And that's where I say we actually see 59% of its surface over its orbit, because it is not in a perfectly circular orbit around the Earth.
Well, the moon is a light in the sky. I don't live on a light, and I'm not in the sky. So
did you know that the moonlight's cold?
Yeah.
So because it's not a circular orbit, that means it's elliptical. Okay. So
it speeds up and slows down.
So it has to speed up and slow down so it doesn't crash into the Earth in order to stay in orbit.
Yeah, I know.
And because of that, the moon will get ahead of us, right? And we will see a little bit of that backside. And then it'll slow down again when it's on its farther side, farther part of its orbit, where it doesn't have to go so fast to stay in orbit. And then we will catch up to it, and we will see a little bit of the front side. And so we will actually see this change in the surface of the moon over a period of one orbit.
Yeah, I can show you cool videos of the moon.
Therefore, it's not a disk, because...
Well, at the horizon, why does it appear to squish? Have you seen that before?
Mm-hmm.
Okay, if it's a sphere, why is it squishing?
Your favorite refraction.
If you actually look at circular lights above you, right, in a hallway, the ones in the distance will appear squished. They're not actually squished, but they appear that way. The sun actually does the same thing. And the sun and moon are both known as lunar and solar disks, right? And I've actually measured the sun with the solar filter shrinking in angular size as it sets, which is impossible on the globe model or paradigm, because you're not getting further away from the sun on a globe when it sets, because it's already 93 million miles away.
So here's a semi-scaled model of what's going on. And so you got the Earth is spinning, the moon is spinning, so one side faces the Earth, tidally locked, right? So the Earth is moving at 67,000 miles an hour, and the moon is staying equally distant. It changes its distance a little bit, but it has to relate to the Earth. So right here, the moon is the moon's moving about 2,000 miles an hour, right? Whatever. So 288. So 2.8 thousand miles an hour. So the moon is going 2,800 miles an hour faster than the Earth right here. Right? So to maintain its distance, it's gonna move forward. Whoops. When it goes to here, it now has to slow down to 67,000 miles an hour. Otherwise, it'll run away from the Earth. So it's slowed down. And then when it goes over here, it has to slow down again to let the Earth pass it. So it has to go down to even slower. And then when it comes over here, it has to speed up again. Otherwise, the Earth will run away. What is making it speed up and slow down?
It's not. It's pretty much the same speed, other than the fact that it's an elliptical orbit. And that's because in the Earth-Moon reference frame, everything else is moving and it's standing pretty much still. So you can stand on the Earth and you can just watch the moon go around you, and it's going to be the same speed because it has to stay in orbit. Now we're assuming a circular orbit, but if it's slightly elliptical, we will see tiny shifts in its speed so that we can see this little bit of the one side versus the other. The next thing I would ask you guys is, why are the shadows curves?
You talking about
shadows curves of what?
Lunar eclipse? You talking about a lunar eclipse?
Phases of the moon. Why is it
phases? Well, I think that it's actually luminescence, I think it's called. I think the moon charges up and charges down.
Yep.
As the sunlight hits it, it transfers that energy into its own light. That'd be a theory. I don't actually know. But the thing is, there's a thing called the Coleridge effect where you can see stars through the moon, right? If it's a solid object, how are you seeing stars through the moon? Even planets, even planets have been seen through the moon. And like Dave's showing there, that's a local light illumination with the moon.
It could also be if it's a NASA image.
This? I
No,
take this picture.
no. I'm saying if what he's talking about is a NASA image, did they screw up? Maybe.
Which one? What do you mean?
The one where you can see the planets through the moon. Did they just?
This is taken by people.
Amateurs have done it.
Yeah. And you've seen the first balloon that NASA sent up and took pictures of the stars and the sun and the moon. It's faker than anything you've ever seen. You've seen that, right?
Well,
but
we already agree that most of everything NASA has ever said or done is fake.
Yeah. So yes. The moon is a dusty, dirty rock, whether you believe NASA or not, in your paradigm. But somehow it reflects light strong enough so I can read by it, cast my shadow on the ground. How is the dusty, dirty rock 238,000 miles away? If we actually did the inverse square law, assuming the moon was only one lumen on a full moon night, when you get to 100 miles from the moon, it would be 60,000 times brighter, which is insane.
That's only if it was its own light source.
No, that's only if it was reflecting or reflecting light. Either way, its own light source. That's if it's at that distance. Or maybe it's right here within our system and it's just a light source within our system. And it's much more than we've been led to believe.
Yeah, you'll see it with your own eyes one day. You'll see that local light illumination in the clouds. I've filmed them many times with the moon. Also, do you know what a solitary eclipse is, Sandy? Have you heard of that before? Okay, well, during a lunar eclipse, according to your paradigm, it's when the sun, moon, and sun are in line, and the sun's basically casting a shadow onto the moon, right? So, but there's a type of eclipse where you can see the sun and moon above the horizon for a single observer, and the moon is still eclipsing, usually from top down, which is the wrong direction.
Right.
So if the Earth is, go ahead.
Yeah, so this viewer can see the sun and the moon above his horizon, and the eclipse can't start, according to heliocentrism, until the Earth is in line. But it does start, and sometimes it comes in from the top. Sometimes it comes in from the bottom. But this time it's coming in from the top, right? That's impossible. So if you want to flip it back at us and go, well, what causes it? We have theories. We don't know. But we can't prove, as you said, science doesn't prove anything, but you can disprove with science for sure. And it's not the Earth causing the shadow on the moon, because the selenium proves that. Disproves
also,
the heliocentric model.
If you get two spheres and you cast a shadow from one to the other, you'll get a distorted shadow. You get an S-wave shadow. That's not what we observe on the moon. We see a smiley face, like just a curved, right? Also, shadows are not red. You guys claim it's like Rayleigh scattering, but the thing is, if it's Rayleigh scattering, the whole entire sky should turn red along with the moon. And then the shadow direction, if you actually look up a time lapse of the shadow on the moon, the supposed shadow, it goes in one way and then it leaves another.
Yeah, it goes in and then it takes a right-hand turn and leaves. And also, when during a solar eclipse, it pauses. Now, that's not what's going on. You got the moon. I dropped my little son. The moon is crossing allegedly in front of the sun. It just keeps on moving, but it pauses, and then it moves.
Yeah,
it pauses.
That's what we see in the solar eclipse. Yeah, it pauses in the middle.
And the other thing
with the solar eclipse shadow, so the moon's claimed to be 2,160 miles in diameter, which is 6 times 6 times 60, the size of America, basically. But during a solar eclipse, that moon that is almost as big as America, or the size of America, is only casting a shadow like 300 miles wide. How do you, if you get an object and use a light to cast a shadow onto that object, onto a wall, say, how does it get smaller? How does the shadow become smaller? Usually what we observe is it's either the same size or bigger. It can never be smaller.
Something to think about. And also, we just had our meteor showers. I think it was the Perseus meteor showers yesterday or whatever. Meteors only go down, but on a globe, if us in the north see them going down, people in the south would see that same meteor going up. No one has ever seen a meteor going up. No one's ever seen. So in the south, these would be meteors going down, but then we would, if we can see that same meteor, it would be going up. No one has ever seen that. Meteors only go down.
Well, the meteors aren't on their original trajectory when they enter our atmosphere. They're being pulled in by gravity, in my theory.
That's your theory, and that things burn up, right? And they're grains of sand. The Perseus meteor showers happens at the same time in August every year, and we're told that it's the Earth traveling through the trail that a comet had left all this dust years and years and years ago. But we're corkscrewing through space, traveling 4.5 billion miles a year, never to return to where we were before. But somehow that comet trail is following the exact trajectory of the Earth, and we pass through the tail at the same time every August.
The comet is also in orbit around the sun.
And it's matching the Earth's movements. It just perfectly. Everything just goes perfectly. Do you see how much blind faith that you have that keep this heliocentrism, alive? It's a lot of blind faith.
Have you heard of the three-body problem, Sandy?
Mm-hmm.
Yeah, I mean, major problems there. They can't simulate three bodies orbiting each other, yet there's hundreds in the solar system, allegedly, that they're working perfectly.
Everything works perfectly. We had a lineup of all the planets. I think it's happening now, where they're all lined up in the sky. How come Jupiter doesn't tug on us? How does the sun, made of helium and hydrogen that defy gravity and defy natural law by collapsing, hold on to Pluto? But when our moon comes around the Earth towards the sun, it doesn't speed up and slow down as it goes away. That's just blind faith to go, well, the sun's gravity, the Earth's gravity holds the moon and it negates the sun's gravity. The sun can hold on to Pluto, but it won't affect our moon. Gravity is gravity in your world.
It does. Well, no, gravity is infinite. So right now, you and me and everybody on this Earth are being pulled by a butterfly trillions of light years away. We just don't feel it because everything else around us is bigger.
Does the sun's gravity affect our moon?
Yeah.
Okay. So does the sun's gravity hold on to Pluto?
Yeah.
Okay.
And the Pluto's gravity holds on to the sun.
So we got the sun over here and we got the Earth here.
Mm-hmm.
And the moon's coming around the Earth. Is the sun's gravity affecting the moon?
It's always affecting the moon.
So is it pulling the moon?
It could.
It could, or it does?
Well, it depends on what part of the orbit we're in.
So we're here heading.
But I mean, it's always pulling.
We're heading towards the sun.
Let me rephrase that. The sun is always pulling on the moon, and the moon is always pulling on the sun.
So can you say that the moon would speed up and then slow down when it goes the other way?
Tiny bit, yeah.
Tiny bit. And so all of these planets and everything else, all of gravities, everything's pulling, but the three-body problem doesn't happen. Do you see the blind faith that you're having? You're saying because it is, therefore it has to work. Therefore, the three-body problem does not apply to actual space. It only applies in computer simulations.
No, it's always applicable.
Well, how come the sky is a perfect clock?
Work.
The sky is a perfect clock.
Only if you have the program.
That was the problem. Sky is a perfect clock. The sky is more accurate than any Swiss watch. The sky clock is what time is.
Do you remember Ptolemy?
Sky clock.
You remember Ptolemy?
Yeah.
Do you remember him? Did you ever meet him?
Ptolemy. So he came up with this thing called epicycles to explain why the outer planets past Earth, Mars, Jupiter, etc., sometimes have retrograde motion, meaning in their orbit, they will look like on our sky they're
Going backwards. Yeah.
But not Mercury and Venus, because they're inside Earth's orbit around the sun. And so that indicates that the Earth is passing them. Again, this is in the theory. And it's going faster because the Earth is closer to the sun. It has to have more velocity to not hit the sun because gravity is higher. Mars is going slower. Jupiter's going even slower, et cetera, all the way out. And that's why their orbits, take so long for them to go around.
Yeah.
So Ptolemy came up with, no. We are the center of the universe and everything's going around us. And the reason why Mars and Jupiter do this thing is because of this called epicycles, where he just tacked on this approximation to make these guys go backwards every once in a while.
Have you seen what the planets' patterns look like? Have you got that, Dave, to show her?
Yeah, I do.
Yeah, they're squiggles. Yeah,
they're perfect. They're perfect.
Perfect circles or ellipses.
Yes,
they're
they
squiggles.
Yes, they are. They're perfect geometric patterns.
Yeah, they're perfect geometric patterns. So let me ask you a question. So Polaris is our North Star right now. And it's not really a special star. It just happens to be lined up with our right. So let's say that there's people on all these other planets in our solar system. Polaris is not an important star to them because their axis is pointing somewhere else, right? So let's say here we are, not to scale. Don't jump down my throat. So let's say Polaris is up here, right? So all of these other planets have different, or Polaris could be over here. It doesn't matter, right? All these other planets, like let's say this one's rotating this way. It's kind of pointing at the sun, and what is this? Jupiter is pointing towards this one, and Saturn's pointing towards this one. Makes sense. So your star, your North Star, is only important to your planet, right? Agreed?
Agreed.
Okay. So why is it? No, and all the planets circle the sun, right?
The same direction.
Same direction. But the moon goes in the opposite direction.
No.
The moon's orbiting the Earth in the same direction?
So in physics, there's a right-hand rule, whereas if you go in the direction of the rotation or the orbit, then this will always point the same direction, and all of these guys go that way.
All right.
One exception is Uranus.
So my point is, when we look at all the planets and all the objects, including Juno, which is an asteroid, they all make perfect spirograph patterns around Polaris. They're all circling Polaris. Polaris is not to them, but they're all circling Polaris. The sun circles Polaris.
The reference frame is the Earth.
Everything circles Polaris. Halley's Comet, everything circles Polaris.
Your reference frame is the Earth.
Yeah, because we're the center of creation. Yeah, we're the center of creation.
Yeah, we're the center, and Polaris, everything circles Polaris in our sky. We're stationary. We're not.
That's all we observe. Yeah, our position is we don't move, and we're the center of creation. So that's why everything rotates around Polaris.
My theory would say that because you're using the Earth as the reference point to do this calculation, of course Polaris is going to come into play because Polaris is important to the Earth.
But you just said the other planets would have different pole stars.
Why are they circling Polaris?
Like I just said, your reference frame is the Earth to do this calculation. Yeah. And so because Polaris is important to the Earth, you are superimposing the importance of Polaris on this calculation.
Would you agree that if in fact we were the center of creation, then that would make a lot of sense that all the planets are just revolving around us?
Planets, whatever they are. I call them wandering stars, fallen angels, whatever you want. But it would make sense.
No, I completely understand the theory.
Okay.
Would you agree that if we could prove we are not moving, then we are the center of creation because that's what it appears to be?
It's possible, except I have friends that used to work at Area 51 who have told me the littlest pieces of what they know and think and have seen, and they can tell me that there's so much stuff outside of this planet.
Well, there's lots of stuff outside. I agree. There's tons of stuff. All right. And
Like living beings.
well, living
So
beings.
I don't know how much we're the center of anything.
Well, hold on. So again, we don't need to speculate what's beyond where we're allowed to go to figure out, to figure out that the Earth is flat. But what if the Earth was like this? What if we're here, America, South America, right? What if this is Antarctica? You can go to Antarctica. There's bases all the way around here, right? And what if there's extra land out here, more land with other civilizations out here, right here?
I've heard that theory.
Right on flat Earth, right? So
I've heard that.
they're here in our system, day trip, not billions of light years or trillions of miles, a trillion miles. You know how long it would take to go a trillion miles at a mile per second? It would take a trillion years, which is a trillion seconds, which is 31,000 years. Okay. And there's no star even that close to us. It's 5 light years, whatever. It's 25 trillion miles is the closest star. So when your people at Area 51 say that there's other beings, other places, what about here? What about that? So here, let me ask you a question. I'm not calling your friends liars, trust me. Can people lie? Absolutely. Can people be fooled? Absolutely. Can people be brainwashed? Can people be tricked? Absolutely. Okay. Testimony from somebody that says that there is something from Area 51, they're probably not lying, but could be one of the other things.
Sure.
Okay. So it's not,
You didn't hear me say with 100% truth. No. This is just something that I was told.
No. Yeah. Are you familiar with, by the way, the Prague clock? The oldest clock in the world?
Prague as in the city in Europe?
Yeah.
Yeah.
The Prague clock, this clock right here.
Yeah.
Right. So this is the oldest clock in the world. And let me just zoom in. And it shows the whole cycle. It has this weird flat Earth map on it, which kind of, I don't want to get into it, but oldest clock in the world. They changed it just recently, and they changed it from the flat Earth map to a globe without telling anybody, without any permits, without any discussion with historians. They changed it from what it was from the oldest clock in the world, and they changed it to this. Does that mean that, they're correcting history, or are they hiding history?
Yeah.
That's a good one. I don't know.
Also, there's the Antikythera mechanism, which shows all the luminaries moving over a flat plane in a circle, just like that clock there. And yeah, the Prague clock, if you look up videos about it and how it works, it's funny how they claim, the funny thing is though, they're saying the sun is moving and the moon is moving and the earth's the center. But that's actually not right. But it actually is a perfect map and a clock. It shows the actual positions of the sun and moon, the phases, and that mechanism there can predict lunar eclipses and solar eclipses on a flat geocentric style Earth.
And it's over 2,000 years old, and it's predicting everything perfectly. Nothing's changed. Three-body problem doesn't exist, right? Everything just works perfectly in the gravitational sky. So, our position is we've all been lied to on a massive scale beyond what most people are willing to admit. Flat earthers are accused. We're going to wrap this up of never be willing. You'll never change your mind. You're a stupid flat earther, right? No, we changed our mind. We were the ones that changed our mind. And people say, why would they lie? And my answer is because they're hiding God. They're hiding that we're at the center of creation. They're hiding our true potential. They're hiding more technology. They're hiding our history. They're hiding possibly more land. They're hiding our divinity. They're hiding our true power. We are incredible, spiritual, powerful beings, and that are all connected. Just as you said, gravity is infinite. Well, our minds are infinite within this realm. And what they do is they cap us off. They put us on a ball, which is limited and fear. It's based in fear. It's based in nonsense, right? And if they can keep you on the ball, they can control you with all sorts of stuff. They can convince you to give away half your income. They can convince you to abide by their rules and not God's law, right? They take you off of God's world and they put you on their world, and he who creates it owns it, and then you have to abide by their rules. So that's what's going on for when the why the lie comes up. Angels, you want to add on, and then we can kind of just bring this to a wrap. Sandy, you've been a very good sport.
Yeah, I mean, we are the sense of creation. The Earth is a flat, geocentric plane, and the luminaries move above us east to west. That's what we observe, and provably that's what it is. It's very easy to prove. You don't need to debate or argue with flat earthers. All you need to do is get a high-power zoom camera on a clear day and do an observations over the horizon. You don't need to point these high-power optics to the sky. You can actually point them to the horizon. And when you do, you'll see too far.
Right.
And you'll see that there's no curvature.
You have to show 66 feet of curvature over a 10-mile lake. Well, we've done way farther than that. But 66 at a 10-mile lake, you can do on even a not perfectly clear day. And we can see the beach 10 miles away. And that's impossible on a ball. Impossible. Sandy, any final comments? And I wanna just wrap up by saying, flat earthers, only constructive comments, information. Anyone that attacks Sandy, I'm going to ban you, and you're never going to be able to comment on my channel again. All right? Flat earthers are very passionate, and they get very passionate. So I don't want you to go, you flat earthers, you're all crazy. I want everybody chill out, leave constructive comments. If you think that we didn't tell her something, leave some comments. Maybe she'll read them. Okay?
So my closing comment would be that the powers that are trying to divide us are doing an excellent job. And for all the foolery that's been going on, whether it's on my side, the globe theory side or the flat earth side, we honestly don't know, because a lot of the things that we've just quoted come from other people or other observations. And the biggest thing is that we can't be divided, especially not at this point in human history. We have to come together. We have to figure out how to get rid of the evil that's doing this to us. And so if we just stay calm, we compare notes, and we try to figure out what's really going on and how to work together, I think that's where we're all headed. And that's the positive thing we pull out of something like this.
I agree. And the reason that Angel and I really push the flat earth thing is because it grounds you. It brings you, it has your feet planted on the ground. If you're spinning out of control, living in a world of fear, believing in all the nonsense, believing that there's a spaceship coming in November and all the wars, everything, all the stuff that they put out there, you're living in fear. When you're in fear, you are not living to your full potential. So why does flat earth matter? Because all of the other atrocities on the world, all of the other nonsense are because people are lost in space, spinning out of control, don't know where they are or who they are.
That's a good way to end.
All right. Angel, you good?
Yeah, well, good. Thanks for that.
Sandy, thanks for coming. I appreciate it. And you've been a great sport. And everybody, be nice. All right. Bye, Sandy.
All right.
Thank you. Take care.
Bye-bye.
Bye.
Good job holding it together.
Yeah, damn. She was super indoctrinated.
She's honest, though. She's being honest, but not intellectually honest. I mean, she's not lying from her point of view.
No.
She's just very indoctrinated. It happened.
She just really wants to believe that refraction's doing all these magical things.
Did you see all the stuff that she had to just, the Georgia Guidestones, like, hey, we made a video, rock solid evidence that the world is not tilting. It was going viral. They blew up the. No, it must be something else.
Yeah.
It's got to be something else.
Even with all the observations, it's got to just be refract. It can't be the Earth is flat. It's got to be something else. It was like that for pretty much everything. Yeah.
Yeah, it was wild. It
was all right, but
I'm gonna upload this right away. So I'll send you a link.
Yeah, we stumped her pretty good the time. Like I did. Like I noticed
all she was doing was making there has to be another excuse. You know what? I used to be that way. When someone says something, I'll just make something up because it has to be, because what you're saying can't be true, and so you'll just make something up.
Yeah, exactly. Yeah,
it's wild.
Yeah, it's amazing how attached people are to the globe. I can't me being young, I wasn't attached like that. Like I wasn't attached to the globe at all. Like
she's highly educated, was in the military, it's just it's a lot. It's a lot to switch your position. I think it's nothing. This isn't a sexist comment, everybody. Chill out. People build a safe world of a belief around them. And women like to build a nice, strong, belief system, and to break out of it, that's harder for them than for men. I think. Yeah. It's nothing against women.
But I think also sometimes it's much harder to get someone to switch to flat Earth or look at the flat Earth when they're older. The more years they've spent indoctrinated, the harder it is to get out. I think at times.
I think you might be right. There is a weird curve, because like young teenagers are really hard. Then it gets easier in your 20s, your late 20s, 30s, and 40s, and then after that it gets harder again.
Yeah, exactly. Yeah, I'd agree. Yeah.
Interesting.
Yeah.
All right. What time? Where are you? It's let me 9 a.m.
9:30. Yeah.
9:30 a.m. There you go.
Yeah.
How does that work on a flat Earth?
With a local sun. Yeah. No, that was good, Dave.
All right, that was good. I'll see you on.
I'll see you around.
Live. Hey, Angels of Light, everybody on TikTok. Make sure you follow him. You can find him on the app. If you hit the star button, if you forget, he's where is he? In the second row? Third?
I think so.
You're in the third row. There you go. Right there. Third row.
Yeah.
Awesome. And just follow him. He does lives. I jump on his lives a lot on TikTok. If you don't have TikTok, you got to get it, because that's where the most of the new stuff is these days. So.
Yeah. Thank you. Take care, guys.
Yeah.
Hey everyone, if you enjoyed this interview, please help support my work and help wake up others by referring or gifting the app to at least one person today. By doing that, you're going to help wake people up and help me to continue doing other interviews like this. With the censorship out there that's going on, it's very difficult to find relevant information. And the app, as you know, brings people to the truthful information of our world. So help support my work, help support your efforts in waking up friends, family, and strangers. Gift them the app or just recommend the app. And let's make 2025 the year Flat Earth breaks free. Check the links below for information on how to gift the app or just refer the app to others and use your referral code to earn Dome cryptocurrency, and a free subscription. Thanks.